Welcome to Echo of Dream Lab, where better sleep begins with science. Welcome to a journey through the silent darkness of our solar system. Tonight, we travel together to one of the most extraordinary places ever discovered by human science. A tiny frozen world, hiding beneath its icy surface, an ocean that may harbor the ingredients for life itself. This is the story of Enceladus. Close your eyes for a moment and imagine yourself floating in the cold vacuum of deep space. You are 886 million miles from the sun. That's more than 9.5 times the distance between Earth and our star. Here, in this remote corner of our solar system, the sunlight is 100 times dimmer than the light that bathes our home planet. The temperature of space around you hovers just above absolute zero. The temperature of space around you hovers just above absolute zero at minus 454 degrees Fahrenheit. At this distance, the sun appears as little more than a very bright star, no larger than a pinpoint in the vast darkness. Before you hangs Saturn, the ringed giant, with its magnificent bands of amber and gold. The planet is so immense that if you could line up 9 Earths side by side across its equator, they would barely span its diameter. Saturn measures 74,898 miles across, a world of swirling gases and perpetual storms that dwarf anything found on Earth. Surrounding this gas giant are the most spectacular rings in our solar system, made of billions upon billions of particles ranging in size from tiny grains of sand to massive boulders the size of houses. These rings stretch outward from the planet for hundreds of thousands of miles. When you see them from this vantage point, they appear as gossamer bands encircling the pale yellow sphere. But Saturn is not alone in its orbit around the Sun. Accompanying this majestic planet are at least 83 moons, each one a world unto itself. Some are large, like Titan, with its thick atmosphere and methane lakes. Others are small, irregular chunks of ice and rock captured by Saturn's immense gravity eons ago. And then there is Enceladus, named after a giant from Greek mythology, one of the ancient gigantes who fought against the Olympian gods. This small world was first discovered on August 28, 1789, by the astronomer William Herschel. Herschel was a remarkable man. Born in Hanover, Germany in 1738, he came to England as a young musician, but his true passion lay in astronomy. Using telescopes that he built himself, grinding and polishing the mirrors by hand in his workshop, Herschel systematically surveyed the night sky with a dedication that bordered on obsess. On that late summer evening in 1789, using his handcrafted 40-foot telescope in Slough, England, Herschel spotted a faint point of light near Saturn that had not been recorded before. He noted its position carefully in his observing journal. Over the following nights, he watched as this point of light moved relative to the background stars, confirming that it was indeed a moon orbiting Saturn. Herschel had discovered 2 Saturnian moons that same year. The other, which he found just 1 month earlier, on July 28th, was Mimas. But neither of these discoveries could compare to his greatest triumph 8 years earlier, when he discovered Uranus, the first planet to be found since ancient times. For over 2 centuries after Herschel's discovery, Enceladus remained little more than a dim speck in even the most powerful telescopes. Scientists could determine its approximate size and brightness, but little else. They knew it was small, with a die of only 313 miles. To put that in perspective, this tiny moon is smaller than the state of Texas. If you could drive completely around Enceladus at highway speeds, never stopping, it would take you about 16 hours to complete the circuit. Enceladus is the sixth largest of Saturn's moons, but it is dwarfed by the giant Titan, which is 10 times larger in diameter. 7 Enceladuses placed side by side would roughly equal the diameter of Earth. In terms of volume, you could fit 722 Enceladuses inside our planet. The surface area of this tiny world is just 1/10 the area of the Mediterranean Sea. It's a small place by any cosmic measure. For most of human history, Enceladus seemed utterly unremarkable. Just another frozen, lifeless chunk of ice, orbiting Saturn in the cold and dark. There were so many more interesting things to study: Jupiter's volcanic moon Io, Saturn's own Titan with its thick, smoggy atmosphere. Mars, with its ancient riverbeds and polar ice caps, seemed far more worthy of scientific attention. But as we would learn, appearances in the cosmos can be profoundly deceiving. Sometimes the smallest, most unassuming worlds hold the greatest secrets, and Enceladus, as it turned out, was keeping secrets that would revolutionize our understanding of where life might exist in our solar system. Chapter 2. The Cassini mission begins. Everything began to change on October 15th, 1997. On that autumn morning at Cape Canaveral Air Force Station in Florida, at precisely 4:23 a.m. Eastern Daylight Time, a massive Titan 4B rocket ignited its engines. The launch pad lit up with an intensity that turned night into day. The roar of the engines, producing over 4 million pounds of thrust, could be heard for miles across the Florida coast. Slowly at first, then with increasing speed, the rocket lifted off, carrying with it one of the most space missions ever conceived. Riding atop this pillar of flame was the Cassini spacecraft, along with its companion, the Huygens probe. Together they weighed nearly 12,500 pounds, making this the heaviest planetary probe ever launched by humanity up to that time. Cassini was named after Giovanni Domenico Cassini, the Italian-French astronomer who discovered 4 of Saturn's moons in the 17th century, as well as the division in Saturn's rings that bears his name. The Huygens probe honored Christian Huygens, the Dutch astronomer who discovered Titan and was the first to describe Saturn's rings accurately. The spacecraft itself was a marvel of engineering, the product of more than 15 years of planning and construction. It measured 22 feet in length and 13 feet in width. At launch, fully fueled, it weighed as much as a school bus. The main body of the spacecraft, called the bus, was hexagonal in shape, built around a framework of aluminum and composite materials designed to withstand the harsh environment of space and the intense radiation near Saturn. Cassini carried 12 scientific instruments designed to study Saturn, its rings, and its moons in unprecedented detail. These included cameras capable of seeing invisible light, infrared, ultraviolet wavelengths. There were instruments to measure magnetic fields, detect particles and cosmic dust, analyze the composition of gases and plasma, and map gravitational fields. There was even a radar system to peer through clouds and haze. 3 plutonium-powered generators provided the spacecraft with electricity. Solar panels would have been useless at Saturn's distance from the Sun, where sunlight is 100 times weaker than at Earth. Instead, the heat from the natural radioactive of plutonium-238 was converted into electrical power, providing about 880 watts of continuous power throughout the mission. The journey to Saturn would not be quick or direct. The spacecraft did not have enough fuel to simply point itself toward Saturn and fire its engines continuously for 7 years. Instead, the mission planners designed an intricate path through the inner solar system, using the gravity of other planets to boost Cassini's speed and change its trajectory. This technique, called a gravity assist or gravitational slingshot, had been pioneered in earlier missions, but Cassini's trajectory was one of the most complex ever attempted. The spacecraft would loop past Venus twice, then past Earth, then past Jupiter, each time using the gravity of these planets to accelerate and redirect its path. On April 26, 1998, just 6 months after launch, Cassini made its first Venus flyby, passing within 176 miles of the planet's cloud tops. The spacecraft whipped around Venus at speeds exceeding 27,000 miles per hour, gaining kinetic energy from Venus's orbital motion around the Sun. 1 year later, on June 24, 1999, Cassini returned to Venus for a second gravity assist. Then, on August 18, 1999, it swung past Earth at an altitude of 717 miles, close enough that amateur astronomers could spot it with small telescopes as it raced by. The Earth flyby added another 12,000 miles per hour to Cassini's velocity. The spacecraft then headed outward toward Jupiter, traveling through the asteroid belt without incident, and arrived at the giant planet on December 30, 2000. The Jupiter flyby was spectacular. Even though Cassini was still months away from its primary target, mission scientists used this opportunity to test the spacecraft's instruments and GAT, were valuable data about Jupiter and its moons. The spacecraft passed within 6 million miles of Jupiter, close enough to capture stunning images of the planet's swirling cloud bands, its great red spot, and its volcanic moon Io. The gravity of Jupiter, the most massive planet in our solar system, gave Cassini its final and most powerful boost, increasing its speed by nearly 4,000 miles per hour and bending its trajectory to intersect Saturn's orbit. After traveling 2.2 billion miles through the solar system over nearly 7 years, Cassini finally approached Saturn in late June 2004. But the mission was far from over. In fact, the most challenging part was just beginning. To be captured into orbit around Saturn, Cassini had to slow down significantly. If it maintained its speed, it would simply shoot past the ringed planet and continue on into deep space. Its 7-year journey wasted. On July 1, 2004, at 01 a.m. Coordinated Universal Time, Cassini executed its Saturn orbit insertion maneuver. The spacecraft turned so that its main engine pointed in the direction of its motion. Then, for 96.5 minutes, that engine fired continuously, consuming nearly 2 tons of propellant. As the spacecraft slowed, Saturn's gravity captured it into an elliptical orbit. Cassini was now the first spacecraft to orbit Saturn. The mission's primary objective, 4 years of studying the ringed planet and its moons, could now begin. Mission controllers had designed an orbital tour that would allow Cassini to make dozens of close approaches to various Saturnian moons. Among these was Enceladus, scheduled for its first close flyby in February 2005, just 7 months after orbital insertion. At the time, scientists didn't expect much from this encounter. Enceladus was known to be bright, reflecting almost all the sunlight that hit it, which suggested a surface of ice, but it was small and presumably inactive. Most scientists thought it would be a relatively boring target compared to the larger, more complex moons like Titan and Iapetus. How wrong they were. Chapter 3: First Glimpses of an Active World. On February 17, 2005, Cassini made its first close approach to Enceladus. The spacecraft swooped within 730 miles of the moon's surface. passing over the northern hemisphere. All 12 scientific instruments were active, gathering data as the spacecraft zipped past at thousands of miles per hour. As the images began arriving back on Earth, transmitted across 900 million miles of space at the speed of light, taking over an hour to reach the receiving antennas of the Deep Space Network, scientists gathered around computer monitors at the Jet Propulsion Laboratory in Pasadena, California. What they saw immediately caught their attention. The first thing that struck everyone: how extraordinarily bright Enceladus appeared. In the images, the moon looked almost like a perfect white sphere, so reflective that it hurt the eyes to look at it on a bright computer screen. Scientists quickly calculated that Enceladus reflects approximately 99% of the sunlight that hits it, making it the most reflective object in the entire solar system. By comparison, fresh snow on Earth reflects about 80 to 90% of sunlight. Earth's moon reflects only about 12%, appearing dark gray in color. Even Europa, Jupiter's ice-covered moon, only reflects about 67% of incoming light. The reason for Enceladus's extraordinary brightness soon became clear. The entire surface is covered in pristine, crystalline water ice, not the ancient, darkened ice found on most other moons, slowly contaminated and discolored by billions of years of cosmic radiation and micrometeorite impacts. But fresh ice, clean ice, ice that looked as if it had been deposited recently, at least in geological terms. This was the first hint that something unusual was happening on this small world. The surface temperature measurements from Cassini's composite infrared spectrometer revealed that most of Enceladus's surface is incredibly cold, averaging around -201 degrees Fahrenheit. At these temperatures, water ice becomes as hard as granite on Earth. The ice is so cold that it would shatter like glass if struck with a hammer. But as Cassini's cameras captured more detailed images, revealing surface features and terrain, scientists noticed something peculiar. The northern hemisphere was heavily cratered, scarred by billions of years' worth of meteorite impacts, just as expected for an ancient surface in the outer solar system. Impact craters are like a geological clock. The older a surface, the more time it has been exposed to bombardment from space rock. The more craters accumulate. By counting craters and comparing their distribution to surfaces of known age, scientists can estimate how old different regions are. The northern regions of Enceladus showed crater densities consistent with surfaces that were 3 to 4 billion years old, ancient terrain that had remained unchanged since the early days of the solar system. But the South Pole looked completely different. This region was remarkably smooth, with far fewer impact craters. Some areas appeared almost crater-free. Crater counting suggested these surfaces might be only 10 to 100 million years old. On a moon that had existed for 4.5 billion years, these were essentially brand new surfaces, formed yesterday in geological time. Something was resurfacing the South Polar region, erasing old craters and laying down fresh ice. But what? As the imaging team examined the high-resolution photographs, they noticed 4 prominent features running ack. These were long, parallel fractures in the ice, each stretching for more than 80 miles across the surface. The fractures were roughly a mile wide and about 1,600 feet deep, like enormous trenches carved into the icy crust. In the enhanced color images, these fractures appeared as dark blue-green streaks against the brilliant white ice. The color difference suggested these regions might have a different composition or grain size compared to the surrounding terrain. The imaging team, led by Carolyn Porco, gave these fractures informal names after Middle Eastern cities from the tales of the Arabian Nights. From north to south, they were called Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus. But the team had a more memorable nickname for them. They called them the Tiger Stripes. When Cassini's infrared spectrometer analyzed the temperature of these tiger stripes, it made an astonishing discovery. While most of Enceladus sat at minus 200 degrees Fahrenheit, the tiger stripes were significantly warmer, measuring minus 120 degrees Fahrenheit. Now, minus 120 degrees is still brutally cold by any human standard. Exposed skin would freeze solid in seconds. But for a moon in the outer solar system, billions of miles from the warming rays of the sun, this was remarkably, puzzlingly warm. Saturn's faint sunlight simply could not account for this heat. The amount of solar energy reaching Enceladus's surface is far too weak to create such a temperature difference. The heat had to be coming from inside the moon. But how? Enceladus is tiny. With a diameter of only 313 miles, it has barely enough mass to have meaningful internal heat. Any primordial heat from the moon's formation 4.5 billion years ago should have been lost to space long ago. Radioactive decay of elements in its rocky core might. Some heat, but calculations suggested this would be minimal. Nowhere near enough to explain the warm tiger stripes. The scientists were puzzled, and the puzzle was about to get much more interesting. 1 month later, on March 9, 2005, Cassini made its second close flyby of Enceladus. This time the spacecraft passed even closer, just 310 miles above the surface, directly over the South Pole. As Cassini approached, one of its instruments, the magnetometer, detected something unexpected. This instrument measures magnetic fields, and it had been continuously monitoring Saturn's magnetic field as the spacecraft orbited the planet. Saturn's magnetic field, like Earth's, extends far out into space, creating a protective bubble called the magnetosphere. This field is generated by electrical currents in the planet's interior and normally flows smoothly through the space around the planet. But as Cassini flew past Enceladus, the MAG detected a disturbance. Saturn's magnetic field was being deflected, pushed aside as if something were interacting with it near the moon. On Earth, we see this same kind of magnetic deflection in our upper atmosphere, where the solar wind of charged particles from the sun interacts with our magnetic field, creating the aurora borealis and aurora australis. The data from Cassini suggested that Enceladus might have an atmosphere, or at least some kind of cloud of gas or charged particles surrounding it. But how could such a tiny moon retain an atmosphere? It had practically no gravity. Any gas should escape into space almost immediately. At the same time, another instrument, the Cosmic Dust Analyzer, detected a sharp increase in the number of dust particles as Cassini passed close to Enceladus. Thousands of tiny ice grains were hitting the detector. Where were all these particles coming from? The ultraviolet imaging spectrograph was pointed at a star behind Enceladus. Watching as the moon passed in front of the star from Cassini's perspective. This technique, called a stellar occultation, can reveal thin atmospheres that would be invisible to direct observation. As Enceladus passed in front of the starlight dimmed, but it didn't dim uniformly. The light fluctuated in a complex pattern consistent with starlight passing through a tenuous atmosphere or cloud of gas and particles around the moon. All of these observations, the magnetic deflection, the dust particles, and the occultation data, pointed to the same surprising conclusion. Enceladus had some kind of atmosphere or gas cloud around it, concentrated near the South Pole, and somehow dust and gas were being actively released from the moon's surface or interior. But definitive proof of what was happening would have to wait for the next flyby, scheduled for July 2005. That encounter would change everything. Chapter 4. The Discovery That Changed Everything. July 14, 2005 was one of the most important days in the history of planetary science, though nobody knew it at the time. This was the date of Cassini's third flyby of Enceladus. And this time, the spacecraft would pass closer than ever before, just 108 miles above the surface. The trajectory would take Cassini directly over the South Pole, passing right above those mysterious warm tiger stripes. Every instrument on the spacecraft was primed and ready. This was the last close encounter with Enceladus that had been planned for Cassini's primary 4-year mission. If there were secrets to be discovered, this was the opportunity. The spacecraft's cameras were pointed at the surface, taking the highest resolution images yet of the South Polar terrain. As Cassini approached, traveling at speeds of nearly 15,000 miles per hour relative to the Moon, the images began to resolve finer and finer details, and then they saw it. Rising from the tiger stripe fractures were jets of material shooting upward into space. Towering plumes, brilliant in the sunlight, erupting from Enceladus like geysers on Earth, but on a far grander scale. The plumes stretched hundreds of miles above the surface. Some reached heights of 300 miles or more. They appeared as graceful arcs and sprays, backlit by the sun, looking like enormous fountains of water vapor and ice particles being blasted into the vacuum of space. The images were spectacular, unlike anything seen before in the solar system, except perhaps on Neptune's moon Triton, where nitrogen geysers had been observed by Voyager 2 in 1989. But Enceladus's plumes were far more extensive, and active scientists were stunned. This tiny moon, smaller than Texas, frozen solid at -200 degrees, was actively venting material into space. The plumes weren't smally or minor outgassing. These were massive eruptions, continuous and powerful, carrying tons of material away from the moon every second. As Cassini flew through the plumes, its instruments sampled the material directly. The cosmic dust analyzer measured the size and composition of ice particles. The ion and neutral mass spectrometer analyzed the gases. The ultraviolet imaging spectrograph measured the density and extent of the plumes. The data showed that the plumes consisted primarily of water vapor, making up about 90% of the material. But they also contained other substances: carbon dioxide, methane, ammonia, simple organic molecules like methanol, formaldehyde, and acetylene, and most intriguingly, molecular hydrogen. This was not just frozen water being sublimated from the surface. The composition of the plumes indicated they were coming from deep within the moon, bringing with them samples of materials that had been processed or altered by chemical R. The presence of ammonia was particularly interesting. Ammonia mixed with water lowers the freezing point significantly, like antifreeze in a car radiator. This suggested that liquid water might exist at temperatures well below 0 degrees Celsius inside Enceladus. But the most important implication was simply this: for material to be erupting from Enceladus with such tremendous force, there had to be a significant source of energy inside this small moon, and there had to be liquid water, or at least partially liquid water beneath the ice. The discovery of the plumes was announced to the world at a NASA press conference in September 2005. The news made headlines globally. Here was a tiny moon in the outer solar system, that was geologically active, with geysers erupting into space and possibly harboring liquid water beneath its frozen surface. Scientists quickly realized that the plumes might explain another long-standing mystery: Saturn's E-ring. The planet's outer rings was known to be made mostly of microscopic ice particles. Unlike the main rings, which lie close to Saturn and are made of larger chunks of ice and rock, the E-ring extends far out from the planet, from the orbit of Mimas at 91,000 miles to the orbit of Rhea at 327,000 miles from Saturn's center. Enceladus orbits right in the middle of the E-ring, at a distance of 148,000 miles from Saturn, and the E-ring is brightest and densest at exactly the location of Enceladus's orbit. Computer models had shown that the E-ring is unstable. The tiny ice particles should be slowly pulled down to Saturn by gravity or pushed outward by radiation pressure from sunlight over timescales of just thousands to tens of thousands of years. Yet the E-ring clearly exists today. Something must be constantly replenishing it, adding new particles to replace those that are lost. Enceladus's plumes provided the answer. The ice particles ejected by the plumes were constantly resupplying the E-ring. Most of the particles were moving fast enough to escape Enceladus's weak gravity and go into orbit around Saturn, contributing to the ring. This explained why the E-ring is brightest at Enceladus's orbit, and why its composition matches the composition of the plumes. The entire E-ring is essentially made from material that has erupted from this tiny moon. But knowing that the plumes existed raised as many questions as it answered. Where exactly was the material coming from? Was there really liquid water beneath the ice? If so, how deep was it? How much was there? And most fundamentally, what was powering these eruptions? Over the next several years, as Cassini made more flybys of Enceladus, scientists worked to answer these questions. Each encounter revealed new details and deepened the mystery. Chapter 5: Mapping the Interior. After the discovery of the plumes, mission planners immediately began working to add more Enceladus flybys to Cassini's tour. The primary mission had been designed before anyone knew about the plumes, so most of the original plan focused on other targets like Titan. But this discovery was too important to ignore. Cassini's mission was extended twice, first for 2 years beyond the original 4-year primary mission, and then again for another 7 years. These extensions allowed the spacecraft to make a total of 23 targeted flybys of Enceladus between 2005 and 2015, some passing as close as 15 miles above the surface, practically skimming the moon. Each flyby was designed to answer specific scientific questions. Some focused on imaging the surface in detail. Others measured the composition of the plumes more precisely. Several flybys were designed to measure Enceladus's gravity field, which would provide crucial information about the moon's internal structure. Gravity measurements from spacecraft are subtle and require precise tracking of the spacecraft's motion. As Cassini flew past Enceladus, the moon's gravity tugged on the spacecraft, changing its velocity very slightly. By measuring this change in velocity using the Doppler shift of Cassini's radio signals back to Earth, scientists could determine the strength of the gravity field at different locations. These measurements revealed something surprising. The South Polar region had less mass than expected at the surface. This seemed backwards at first. If there were warm spots and active geology, you might expect extra mass, perhaps from volcanic deposits or upwelling material. But the measurements made sense if you considered what might lie beneath the surface. If there were a body of liquid water underneath the South Pole, this would explain the gravity anomaly. Liquid water is less dense than ice, so a subsurface ocean would create a negative mass anomaly, exactly matching what Cassini measured. In 2014, a team of scientists led by Luciano Ease analyzed gravity data from 3 very close flybys in 2010. Their results, published in the journal Science, provided strong evidence for a regional sea beneath the South Pole. The data suggested that beneath the South Polar terrain, at a depth of perhaps 30 to 40 miles below the surface, there was a layer of liquid water roughly the size of Lake Superior. This subsurface sea was estimated to be about 6 miles deep. The ice shell above the ocean was relatively thin at the South Pole, perhaps only 3 to 6 miles thick, but much thicker, possibly 12 to 18 miles thick, at the North Pole. This explained why the plumes were confined to the southern region. But was this ocean only regional, limited to the southern hemisphere? Or extend around the entire moon? The answer came in 2015 from a completely different line of evidence. A team led by Peter Thomas and Matthew Tiscareno at Cornell University published a study in the journal Icarus that analyzed Enceladus's rotation. Because Enceladus orbits Saturn in a slightly elliptical path, Saturn's gravity exerts changing tidal forces on the moon. These forces cause Enceladus to wobble very slightly as it rotates, a motion called libration. Think of how a spinning top wobbles as it slows down, and you'll have the right idea, though the mechanism is different. The amount of wobble depends on how the moon's mass is distributed inside. If the icy crust were rigidly attached to the rocky core, the wobble would be small. But if the crust were floating on a layer of liquid, detached from the core, the wobble would be much larger. Thomas and his colleagues measured this wobble by carefully tracking the positions of surface feature. Thousands of images taken over 7 years of Cassini observations. They found that Enceladus's libration amplitude was 0.120 degrees, plus or minus 0.014 degrees. This measurement was far too large for the crust to be attached to the core. The only explanation was that the entire icy shell was floating on a global ocean. Enceladus didn't have a regional sea confined to the South Pole. It had a complete ocean encircling the entire moon. Subsequent analysis, combining the gravity data, shape measurements, and libration data, allowed scientists to build a detailed model of Enceladus's interior structure. At the center is a rocky core, probably composed of silicate rock, similar to carbonaceous meteorites, about 120 miles in radius. Surrounding this core is a global ocean of liquid water, perhaps 20 to 25 miles deep on average. At the South Pole, where the ice is thinnest, the ocean might be only 12 to 18 miles below the surface. North Pole, where the ice is thickest, the ocean might be 30 miles down. The total volume of water in this ocean is estimated to be around 40,000 cubic miles. That's roughly equivalent to 42,660 Lake Tahoes, or about half the volume of Lake Superior, the largest Great Lake. For such a small moon, this represents an enormous amount of liquid water. Above the ocean is the ice shell, varying in thickness from perhaps 3 miles at the thinnest points near the South Pole to 18 miles or more at the North Pole. This ice isn't uniform. It likely has multiple layers with different properties, some more brittle, some more ductile, depending on temperature and pressure. The surface temperature of minus 200 degrees makes the uppermost ice extremely hard and brittle. But deeper down, as pressure and temperature increase, the ice becomes more plastic, able to flow slowly over geological timescales like a glacier on Earth. This structure, with a rocky core, a global ocean, and an icy shell, makes Enceladus similar in some ways to Jupiter's moons Europa and Ganymede, which are also thought to harbor subsurface oceans. But Enceladus is much smaller, and its ocean is much more accessible, erupting directly into space through the tiger stripes. Understanding the internal structure was crucial, but it still didn't fully explain how the ocean remained liquid. For that, scientists needed to understand the heat source keeping the ocean from freezing. Chapter 6: The Heat Engine. Enceladus receives almost no heat from the distant sun. At Saturn's distance, solar energy is 100 times weaker than at Earth. The faint sunlight can barely raise the surface temperature above -200 degrees Fahrenheit. It certainly cannot keep a subsurface ocean liquid. Radioactive decay of elements like uranium, thorium, and potassium in the rocky core does generate some heat, as it does inside Earth. But Enceladus is so small that its total radioactive heat production is estimated at only about 0.3 gigawatts, less than half the output of a single large nuclear power plant on Earth. This is nowhere near enough to maintain a global liquid ocean. Calculations show that the heat flux, the rate at which heat flows out through the surface, especially near the South Pole, is at least 10 times higher than what radioactive decay alone could provide. In 2006, Cassini's composite infrared spectrometer measured heat output from the tiger stripes of 3 to 7 gigawatts, possibly as high as 10 gigawatts. To put this in perspective, 10 gigawatts is roughly the power output of 15 large nuclear power plants. Where is this heat coming from? The answer lies in a phenomenon called tidal heating. This is the same process that keeps Jupiter's moon Io volcanically active, creating the most with hundreds of active volcanoes. Tidal heating works through gravitational interactions. As Enceladus orbits Saturn, it travels not in a perfect circle, but in a slightly elliptical path. This ellipticity or eccentricity is small, only about 0.047, meaning Enceladus gets about 1% closer to and farther from Saturn over the course of each orbit. But even this small variation creates significant effects. When Enceladus is at the closest point in its orbit, called periapsis, it is 146,700 miles from Saturn's center. At the farthest point, called apoapsis, it is 149,500 miles away. The difference is about 2,800 miles. When Enceladus is closer to Saturn, the planet's gravitational pull is stronger. When it's farther away, the pull is weaker. This changing gravitational force constantly deforms the moon. Stretching, imagine taking a rubber ball and rhythmically squeezing it in your hand. The repeated deformation would generate heat through friction as the rubber molecules move against each other. The same thing happens to Enceladus, but on a much larger scale. Saturn's gravity generates heat by flexing the moon's interior. The solid ice and rock flex and compress, creating friction. Calculations suggest this tidal heating generates somewhere between 3 and 10 gigawatts of power, perfectly matching the observed heat output. But there's more to the story. If Enceladus's orbit were perfectly circular, there would be no tidal heating. The gravitational force would be constant, and the moon wouldn't be squeezed and stretched. So, what maintains the orbital eccentricity? The answer involves another moon called Dione, which orbits Saturn farther out at 189,600 miles from the planet's center. Enceladus and Dione are locked in what's called a resonance. For every 2 orbits that Enceladus makes around Saturn, Dione makes exactly 1 orbit. This 2-to-1 orbital resonance is remarkably stable. It has persisted for hundreds of millions of years, possibly billions. Every time Enceladus completes 2 trips around Saturn, returning to the same position. Dione is also returning to the same position relative to Enceladus. The gravitational tugs between the two moons always occur at the same points in their orbits. These periodic gravitational tugs prevent Enceladus's orbit from becoming circular. Just as the orbit tries to circularize through tidal interactions with Saturn, Dione's gravity pumps the eccentricity back up, maintaining the elliptical shape. It's like pushing a child on a swing at just the right moment to keep them going. Without Dione's influence, Enceladus's orbit would gradually become more circular over millions of years. Tidal heating would diminish and eventually stop. The ocean would freeze. The plumes would cease. Geological activity would end. But the resonance with Dione keeps the system going, maintaining the conditions necessary for liquid water. This tidal heating doesn't just keep the ocean liquid. It drives the geological activity that creates the plumes. The heat is not distributed evenly throughout the moon. Instead, it's concentrated in certain regions, particularly along the tiger stripe fractures at the South Pole. Computer models suggest that as tidal forces flex the ice shell, they create zones of intense stress along these fractures. The ice cracks and grinds, generating additional heat through friction. This localized heating can create pockets where the ice is near its melting point, or where liquid water can exist in cracks and channels within the ice. The tidal forces also physically open and close the tiger stripe fractures as Enceladus orbits Saturn. When Enceladus is near apoapsis, farthest from Saturn, the fractures open sly, perhaps widening by tens of feet. This allows water and vapor from below to escape more easily, intensifying the plumes. When Enceladus is near periapsis, closest to Saturn, the fractures squeeze shut, reducing the plume activity. Cassini observations confirm this pattern. The plumes varied in intensity over Enceladus's 33-hour orbital period, strongest near apoapsis, weaker near periapsis, just as the tidal model predicted. Understanding tidal heating was crucial because it meant the energy source for Enceladus's ocean was not running out. As long as the orbital resonance with Dione persisted, and as long as Saturn existed, tidal heating would continue. This wasn't a temporary phenomenon. The ocean had likely existed for millions or billions of years, and would continue to exist for millions or billions of years into the future. That long-term stability was important for another reason. If there was any possibility of life in Enceladus's ocean, it would. Time to develop and evolve. A transient pocket of liquid water existing for just a few thousand years would probably not be enough. But an ocean that had persisted for geological timescales, that was a different story. Chapter 7. Chemistry of an Alien Ocean. Understanding that Enceladus had a liquid ocean kept warm by tidal heating was revolutionary. But scientists wanted to know more. What was this ocean made of? What chemicals were dissolved in the water? What was the temperature? And most importantly, could this ocean support life? The plumes provided a direct way to answer these questions. Unlike Europa's ocean, which is buried beneath miles of solid ice with no known way to reach it, Enceladus's ocean was erupting into space, offering free samples that Cassini could analyze. Over multiple flybys, particularly those in 2008, 2015, and the final close encounter in 2017, Cassini flew directly through the PLA, sometimes passing less than 30 miles from the surface. The spacecraft's instruments collected and analyzed the material. The ion and neutral mass spectrometer was particularly valuable for this work. This instrument could identify molecules based on their mass and electrical charge. As plume material entered the instrument, it was ionized and then sorted by mass, creating a signature that revealed what chemicals were present. The most abundant material, as expected, was water vapor, making up about 98% of the gas in the plumes. But the remaining 2% was fascinating. Scientists detected carbon dioxide at about 0.3 to 0.8%, methane at about 0.1%, and smaller amounts of ammonia, molecular hydrogen, and various simple organic compounds. The organic molecules were particularly intriguing. Methanol, formaldehyde, acetylene, propane, and ethane were all detected. These are simple carbon-based molecules, but they're the building B. More complex organic chemistry. In the ice particles, analysis revealed even more complex materials. Macromolecular organic compounds with masses up to 200 atomic mass units were detected, suggesting the presence of larger, more complex organic molecules than simple methane or methanol. The presence of salt in the ice grains, detected as sodium and potassium compounds, indicated that the ocean water was not pure. It was salty, perhaps similar in composition to Earth's oceans, though probably less salty. The exact salinity was difficult to determine, but estimates suggested somewhere between 0.5 and 2% salt by weight, compared to Earth's oceans at about 3.5%. The salt was important because it told scientists that water was interacting with rock. Pure water ice from the surface would not contain salt, but water that had been in contact with minerals in the rocky core would dissolve salts and carry them into the ocean. This meant there was communication between the ocean and the rocky interior, a key requirement for interesting chemistry. But the most important discovery came in 2017, during Cassini's final close flyby of Enceladus on October 28th, just 2 months before the spacecraft's mission would end. During this encounter, Cassini dove deeper into the plumes than ever before, skimming just 30 miles above the surface. The data from this flyby revealed the presence of molecular hydrogen, H2, in significant concentrations, roughly 1% of the plume composition. This was a game-changing discovery. Molecular hydrogen is not found in ice. It's not produced by simple sublimation of frozen material. The only way to get molecular hydrogen in these concentrations is through chemical reactions between liquid water and certain types of rock. On Earth, we see this process at hydrothermal vents on the ocean floor. Hot water, heated by volcanic or tech activity, circulates through cracks in the oceanic crust. This water reacts with minerals containing iron, particularly olivine and pyroxene, in a process called serpentinization. During serpentinization, the iron in the rock is oxidized, pulling oxygen atoms from water molecules. This breaks water apart into hydrogen and oxygen. The oxygen combines with the iron to form iron oxide, essentially rust. The hydrogen is released as molecular hydrogen gas, H2. These reactions also produce heat, which can further drive circulation and chemical processes. And importantly, they create chemical energy that life can use. On Earth, entire ecosystems at hydrothermal vents derive their energy not from sunlight, which cannot reach the deep ocean floor, but from the chemical energy released by these reactions. The organisms at these vents, primarily microbes but also larger creatures that depend on the microbes, use molecular hydrogen and other chemicals as fuel. They combine hydrogen with carbon dioxide or other compounds to produce energy, much as we combine food with oxygen to produce energy. The detection of molecular hydrogen in Enceladus's plumes strongly suggested that similar chemistry was occurring on the ocean floor. Warm water from the ocean was likely circulating through cracks in the rocky core, reacting with the minerals, producing hydrogen, and returning to the ocean, carrying this chemical fuel with it. Computer models of Enceladus's interior suggested that the temperature at the rock-water interface could be quite warm, perhaps 30 to 90 degrees Celsius, or 86 to 194 degrees Fahrenheit. This is exactly the temperature range where serpentinization reactions are most efficient on Earth. The amount of hydrogen detected suggested these reactions were ongoing and vigorous. Calculations indicated that Enceladus might be producing up to 40 tons of hydrogen per year through chemical reactions. For comparison, a single hydrothermal vent field on Earth might produce a similar amount. This hydrogen wasn't staying dissolved in the ocean water. Much of it was escaping through the plumes into space. But before it escaped, it was available as chemical energy for any organisms that might exist in the ocean. Scientists published their findings in the journal Science in April 2017. The paper's title was direct: Cassini finds molecular hydrogen in the Enceladus plume. Evidence for hydrothermal processes. The implications were clear. Enceladus had not just liquid water, but an active chemical system that could support life. But there was still more to discover about the chemistry of this alien ocean. Chapter 8: The Building Blocks of Life. Life, as we know it on Earth, requires several basic ingredients. Liquid water is the first and most fundamental requirement. Water is an excellent solvent, allowing chemicals to dissolve and react. All life on Earth uses liquid water for these purposes. Energy is the second requirement. Life needs energy to power its metabolism, to build complex molecules from simpler ones, to grow and reproduce. On Earth, most life ultimately derives its energy from sunlight through photosynthesis. But in environments without sunlight, like deep ocean vents, life can derive energy from chemical reactions. The third requirement is organic matter. Molecules containing carbon bonded to hydrogen and other elements. These organic molecules are the building blocks of proteins, DNA, cell membranes, and all the other complex structures that life needs. The fourth requirement, often overlooked but crucial, is a set of essential elements beyond just carbon, hydrogen, and oxygen. Life on Earth requires nitrogen, phosphorus, and sulfur at minimum. These elements are incorporated into proteins, DNA, RNA, ATP, and other biological molecules. Without them, life as we know it ceases. By 2017, it was clear that Enceladus had the first three requirements. Liquid water, check. Energy from chemical reactions, check. Organic molecules, check. But what about those essential elements? Nitrogen had been detected in the plumes in the form of ammonia, NH3, and nitrogen gas, N2. Sulfur had been detected as hydrogen sulfide, H2S, and other sulfur-containing compounds. These elements were present in the ocean, but phosphorus remained undetected. Phosphorus is crucial for life. It's a component of DNA and RNA, the molecules that store genetic information. It's part of ATP, the molecule that cells use to store and transfer energy. It's in cell membranes. Without phosphorus, life as we know it simply cannot function. The problem was that phosphorus is relatively rare in the universe compared to other biogenic elements. And in many aqueous environments, phosphorus tends to bind tightly with calcium and other minerals, forming insoluble calm, like apatite that precipitate out of solution. This makes phosphorus unavailable for biological use. On Earth, phosphorus enters the biosphere primarily through the weathering of rocks on land, which releases soluble phosphates that wash into rivers and eventually reach the oceans. But Enceladus has no land surface, no weathering, no rivers. How could its ocean contain accessible phosphorus? For years, this remained an open question. Cassini's instruments had detection limits. If phosphorus was present in low concentrations, below the threshold of detectability, the spacecraft might simply have missed it. Then, in June 2023, 3 years after Cassini's mission had ended, a team of scientists published a remarkable paper in the journal Nature. The team, led by Christopher Glane at the Southwest Research Institute and Frank Posberg at the Free University of Berlin, had conducted a detailed reanalysis of data from Cassini's cosmic dust analyze. This instrument had collected thousands of individual ice grains from the plumes during various flybys. Each grain that hit the detector created a unique signal based on its composition. The team developed new analysis techniques to extract more information from these signals, looking for subtle signatures that might have been overlooked in earlier analyses. What they found was phosphorus, not in all grains, but in a significant fraction of them. The phosphorus was present as phosphates, soluble compounds that could be used by biology. The concentrations were substantial, at least 100 times more concentrated than in Earth's oceans. This was the final piece of the puzzle. Enceladus's ocean contained all 6 essential elements for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. It had liquid water. It had energy from chemical reactions, and the chemistry suggested the ocean was alkaline. With a pH probably around 11 or 12, similar to conditions serpentinizing hydrothermal systems on Earth where life thrives. But how was phosphorus getting into the ocean in such high concentrations? The research team proposed a model based on our understanding of Enceladus's interior structure. The rocky core likely contains phosphorus locked in minerals, just as it is in meteorites and asteroids. Normally, these phosphorus-bearing minerals would react with water to form insoluble calcium phosphates, removing phosphorus from solution. But Enceladus's ocean chemistry was different from typical aqueous environments. The ocean was alkaline and contained significant amounts of carbonate and ammonia. Under these conditions, carbonate ions preferentially bind with calcium, forming calcium carbonate instead of calcium phosphate. This keeps the calcium occupied and prevents it from binding with phosphorus. The phosphorus remains in solution as soluble sodium phosphate, available in the water. Additionally, the models suggested that the ocean might be saturated or supersaturated with certain minerals, creating a kind of soda lake environment similar to alkaline lakes on Earth, like Lake Mono in California. In these Earth analogs, phosphorus is also highly soluble and available. The discovery of abundant phosphorus was published with a title that perfectly captured its significance: Detection of Phosphates Originating from Enceladus's Ocean. The paper concluded with a statement that would have seemed like science fiction just 20 years earlier. Our results provide the most complete chemical analysis to date of an extraterrestrial liquid water body, demonstrating that Enceladus harbors an environment that satisfies all fundamental requirements for life as we know it. As we drift toward sleep, consider this remarkable fact. Orbiting Saturn, nearly 1 billion miles from Earth, there exists an ocean warmed by gravitational forces, enriched with organic molecules, energized by chemical reactions between water and rock, and containing all the elements necessary for life. This ocean has likely persisted for millions or billions of years, perhaps for the entire 4.5 billion year history of the solar system. We have not yet found life in this ocean. We have no direct evidence that any organisms exist in those cold, dark waters beneath the ice. But we have found every chemical precondition that life requires. We have found an environment that on Earth would almost certainly contain life. Enceladus has shown us that the conditions for life may be more common in the universe than we imagined, not just on planets orbiting in the habitable zones of stars, where liquid water can exist on the surface, but in the hidden oceans of small moons, kept liquid by tidal heating, existing in the cold and dark far from the sun. As Cassini's mission came to an end in September 2017, the spacecraft made one final contribution to science. To avoid any possibility of contaminating Enceladus with microbes from Earth that might still be clinging to the spacecraft, mission controllers deliberately directed Cassini to plunge into Saturn's atmosphere, where it burned up completely. The data Cassini collected during 13 years at Saturn, including 23 flybys of Enceladus, will be studied for decades to come. But the spacecraft itself is gone, its atoms now part of Saturn's clouds. The story of Enceladus, however, is far from over. It has only just begun. Excellent work continuing this calm and profound journey alongside Echo of Dreamlab. Close your eyes gently. Now that the locks to Enceladus's initial secrets have been broken, clear your mind for a moment of all earthly lights and sounds. We commence a journey to the deepest and darkest ecosystems of life, to places where sunlight has never ventured. Enceladus is not alone. Across our solar system, short paws hidden beneath ice and rock, liquid water oceans may be surprisingly common. As we drift deeper into our journey tonight, let us explore these other ocean worlds and understand why Enceladus holds such a special place among them. The concept of ocean worlds represents a profound shift in how we think about habitability in the cosmos. For most of human history, we assumed that life required conditions similar to Earth, a rocky planet not too close and not too far from its star, with liquid water on the surface warmed by sunlight. The so-called Goldilocks zone. But discoveries of the past few decades have expanded our understanding dramatically. We now know that liquid water, and potentially life, can exist in places we never imagined. Worlds in the outer solar system, billions of miles from the sun, frozen on the surface, but liquid within. Jupiter, the largest planet in our solar system, has at least 95 moons. Among these, 4 stand out: Io, Europa, Ganymede, and Callisto. These are the Galilean moons, discovered by Galileo Galilei in 1610, when he pointed his primitive telescope at Jupiter and saw what he first thought were stars moving around the planet. Europa, slightly smaller than Earth's moon, has long fascinated scientists. Images from the Voyager missions in the 1970s and 80s showed a surface unlike anything seen before. Instead of heavily cratered terrain like most moons, Europa's surface was remarkably smooth, crisscrossed by a network of dark lines and cracks. The surface appeared to be made of water. Ice, but it was young, geologically active. When NASA's Galileo spacecraft orbited Jupiter from 1995 to 2003, it confirmed what many had suspected. Europa has a global ocean of liquid water beneath its icy crust. The ocean may be 40 to 60 miles deep, perhaps twice the volume of all Earth's oceans combined. The ice shell above is estimated to be 10 to 15 miles thick, possibly less in some regions. But reaching Europa's ocean would be far more difficult than sampling Enceladus's plumes. There are no known geysers erupting from Europa's surface, though recent observations suggest there might be occasional water vapor plumes near the South Pole. The evidence remains tentative, and even if plumes exist, they appear to be intermittent and much weaker than Enceladus's continuous jets. To truly explore Europa's ocean, we would need to land on the surface and drill through miles of ice. This presents enormous technical challenges. The ice is as hard as rock at the surface temperature of -260 degrees Fahrenheit. It would take powerful drilling equipment, heated by nuclear power sources, years to penetrate through to the ocean below. Europa also sits deep within Jupiter's intense radiation belts. The surface is bombarded constantly by high-energy particles trapped in Jupiter's magnetic field. These radiation levels are lethal to humans and damaging to electronics. Any spacecraft on Europa's surface would need heavy shielding and would have a limited operational lifetime. Despite these challenges, Europa remains one of the top priorities for astrobiology. The ocean is in contact with a rocky seafloor. Chemical reactions between water and rock, similar to those on Enceladus, could provide energy for life. The tidal heating from Jupiter, even stronger than Saturn's effect on Enceladus, keeps the ocean liquid and may drive hydrothermal activity. NASA's Europa Clipper mission, launched in October 2024, is currently on its way to Jupiter. It will arrive in April 2030 and conduct dozens of flybys of Europa, studying the ice shell, searching for plumes, measuring the ocean's depth and salinity, and assessing the moon's habitability. This $5 billion mission represents one of NASA's highest priority objectives in planetary science. If Europa Clipper detects active plumes, future missions could fly through them and sample the ocean water directly, just as Cassini did at Enceladus. If not, the next step might be a lander mission that could study the surface composition and perhaps eventually drill through the ice. Ganymede, Jupiter's largest moon and the biggest moon in the entire solar system, is even larger than the planet Mercury. It also has a subsurface ocean detected through measurements of its magnetic field by the Galileo spacecraft. But Ganymede's ocean lies beneath perhaps 90 miles of ice mixed with rock. It's far less accessible than Europa's or Enceladus's oceans, and there's no evidence of communication between the ocean and the surface. Callisto, the second largest Galilean moon, may also have a subsurface ocean, though the evidence is less certain. Like Ganymede, any ocean would be buried beneath many miles of ice and rock, making it a lower priority for near-term exploration. Saturn's largest moon, Titan, is another ocean world, but of a very different character. Titan is the only moon in the solar system with a thick atmosphere, even denser than Earth's. The surface temperature is minus 290 degrees Fahrenheit, cold enough that water ice is as hard as rock, but Titan has seas and lakes of liquid methane and ethene on its surface. The only known surface liquids in the solar system beyond Earth. Beneath Titan's icy crust lies a global ocean of liquid water mixed with ammonia, perhaps 50 to 60 miles below the surface. The Cassini mission detected this ocean through measurements of Titan's shape and how it changes due to tidal forces from Saturn. But Titan's subsurface ocean is probably isolated from the surface by a thick shell of ice and high-pressure ice polymorphs. It may not be in contact with rock, which would limit the chemical energy available for life. Titan is interesting for different reasons. The surface environment, with its organic chemistry and liquid hydrocarbons, might support exotic forms of life based on completely different biochemistry than Earth's water-based life. Titan represents an entirely different approach to habitability, one that scientists are only beginning to explore. Neptune's moon Triton, captured by Voyager 2 during its flyby in 1989, showed signs of geological activity, including nitrogen geysers. Some scientists believe Triton may have a subsurface ocean of liquid water mixed with ammonia, perhaps 50 to 60 miles below the surface. The Cassini mission detected this ocean through measurements of Titan's shape and how it changes due to tidal forces from Saturn. But Titan's subsurface ocean is probably isolated from the surface by a thick shell of ice and high-pressure ice polymorphs. It may not be in contact with rock, which would limit the chemical energy available for life. Titan is interesting for different reasons. The surface environment, with its organic chemistry and liquid hydrocarbons, might support exotic forms of life based on completely different biochemistry than Earth's water-based life. Titan represents an entirely different approach to habitability, one that scientists are only beginning to explore. Neptune's moon Triton, captured by Voyager 2 during its flyby in 1989, showed signs of geological activity, including nitrogen geysers. Some scientists believe Triton may have a subsurface ocean, though this remains speculative. Triton is notable for orbiting Neptune in a retrograde direction, opposite to the planet's rotation, suggesting it was captured from the Kuiper Belt. This violent capture would have generated enormous heat, possibly enough to melt the interior and create an ocean that might persist today. Even Pluto, the dwarf planet at the edge of the solar system, may have an internal ocean. NASA's New Horizons spacecraft, which flew past Pluto in 2015, found evidence of recent geological activity on the surface. The presence of Sputnik Planitia, a vast plain of nitrogen ice, and its alignment with Pluto's tidal axis, suggests there may be a liquid water ocean beneath the ice. The ocean would need to be partially frozen and slushy to explain the observations. But it's remarkable that even at Pluto's distance from the Sun, more than 3.5 billion miles, liquid water might exist. Among all these ocean worlds, Enceladus stands out for several reasons. Its ocean is accessible through the plumes, allowing direct sampling without drilling. The plumes show clear evidence of hydrothermal activity and complex organic chemistry. The moon is geologically active, with energy flowing from the interior, and it's small and nearby, at least compared to worlds like Europa, making it a relatively easier target for future missions. But Europa is also compelling, with its much larger ocean and stronger tidal heating. The debate over which world, Enceladus or Europa, should be the priority target for a life detection mission continues among scientists. Both worlds deserve thorough exploration. Both might harbor life, and discoveries at either world would transform our understanding of biology and our place in the universe. Chapter 10: Life in the Dark. To understand whether life could exist on Enceladus or other ocean worlds, we must first understand how life survives in Earth's deepest, darkest environments. Let us travel now to the bottom of Earth's oceans, to places where sunlight never penetrates, and discover the extraordinary forms of life that thrive there. In 1977, scientists aboard the research submersible Alvin were exploring the Galapagos Rift, a volcanic ridge on the ocean floor about 2.5 kilometers beneath the surface of the Pacific Ocean. They were searching for hydrothermal vents, places where hot water from beneath the Earth's crust erupts onto the seafloor. What they discovered changed biology forever. Surrounding the vents, in total darkness, far from any energy from the sun, they found thriving ecosystems. Giant tube worms, some growing up to 8 feet long, massive clams, blind crabs and shrimp, bacterial mats coating the rocks in thick white carpets. Life, abundant and diverse in a place where life should not be able to exist. For billions of years before plants evolved, all life on Earth survived without photosynthesis. But even after photosynthesis evolved and transformed Earth's atmosphere, these deep-sea communities continued to live as they always had, independent of the sun, deriving their energy from chemistry rather than light. The hydrothermal vents on Earth come in different types. Black smokers emit superheated water at temperatures exceeding 700 degrees Fahrenheit. The water is loaded with dissolved minerals, particularly sulfides of iron, copper, and zinc. When this scorching water meets the near-freezing ocean water, the minerals precipitate rapidly, forming dark clouds that look like smoke and building chimneys of mineral deposits that can grow dozens of feet tall. White smokers emit cooler water, typically between 150 and 300 degrees Fahrenheit. These vents produce white or light-colored mineral deposits, primarily calcium carbonate and silica, along with dissolved hydrogen, methane, and other reduced compounds. The chemistry occurring at these vents is driven by the interaction between seawater and hot rock. As seawater seeps down through cracks in the ocean crust, it is heated by magma chambers below. The heated water becomes acidic and reactive, leaching minerals from the surrounding rock. Chemical reactions strip electrons from iron and other metals, producing hydrogen gas and reducing sulfates to sulfides. When this altered, chemically rich water rises back up and erupts at the vents, it carries with it dissolved hydrogen, hydrogen sulfide, methane, ammonia, and other reduced compounds. These are the fuels that power life at the vents. Microorganisms called chemolithotrophs, literally rock eaters, harvest the chemical energy from these compounds. They use dissolved oxygen in the seawater to oxidize hydrogen, or hydrogen sulfide, or methane, extracting electrons that they can use to power their metabolism, just as we use electrons from glucose to power ours. These microbes form the base of the vent ecosystems. Some are free living, floating in the water or forming mats on rocks. Others live in symbiotic relationships with larger animals. The giant tube worms, for example, have no mouth or digestive system. Instead, they harbor chemosynthetic bacteria inside specialized organs in their bodies. The tube worms provide the bacteria with hydrogen sulfide from the vent water, which they collect through their bright red plumes. The bacteria use this hydrogen sulfide to produce organic molecules that nourish the worm. It's a perfect symbiosis, allowing both partners to thrive in an otherwise hostile environment. Similar chemosynthetic ecosystems exist at cold seeps, where methane or hydrogen sulfide seeps out of the seafloor at near ambient temperatures. At these locations, different types of microorganisms consume methane directly, often in partnership with sulfate-reducing bacteria. These methane-consuming microbes, called methanotrophs, are found worldwide, from Arctic permafrost to deep-sea sediments. Some of the most fascinating chemosynthetic organisms are the methanogens, microbes that produce methane as a byproduct of their metabolism. Methanogens are archaea, not bacteria, representing one of the three domains of life on Earth. They are found in diverse environments: the guts of cows and termites, wetland sediments deep underground in rock formations, and of course at hydrothermal vents. Methanogens use hydrogen gas to reduce carbon dioxide to methane, releasing energy in the process. This metabolism, called methanogenesis, is ancient, possibly dating back to the earliest life on Earth more than 3.5 billion years ago. It doesn't require oxygen, which didn't exist in Earth's early atmosphere. It doesn't require sunlight. It only requires hydrogen, carbon dioxide, and a suitable environment. This is why the detection of hydrogen in Enceladus's plumes was so significant. Hydrogen is the fundamental fuel for chemosynthetic life. Its presence, along with carbon dioxide, methane, and other organic compounds, means that methanogenesis and similar metabolic processes could occur in Enceladus's ocean, just as they do in Earth's deep seas. But could life actually survive in an environment like Enceladus? The conditions are extreme by any measure. The pressure at the seafloor, with 20 miles of ocean above and several miles of ice on top of that, is enormous, perhaps 2,000 atmospheres. The temperature ranges from near freezing in most of the ocean to possibly 80 or 100 degrees Fahrenheit near hydrothermal vents, if they exist. Life on Earth, however, has shown remarkable adaptability to extreme conditions. Microorganisms called extremophiles thrive in environments that would kill most other forms of life. Thermophiles live in boiling hot springs at temperatures up to 230 degrees Fahrenheit. Psychrophiles live in Antarctic ice at temperatures well below freezing. Barophiles live at the bottom of the Mariana Trench under pressures exceeding 1,000 atmospheres. Some microorganisms called polyextremophiles can tolerate multiple extreme conditions simultaneously. For example, Thermococcus barophilus, discovered at a deep-sea hydrothermal vent, thrives at temperatures around 175 degrees Fahrenheit and pressures of 400 atmospheres. Remove either the high temperature or the high pressure, and it won't grow. The key point is that life is not fragile. Once it gets started, it's incredibly tenacious. It adapts to whatever conditions are available. If liquid water exists, if chemical energy is available, if the basic elements are present, life finds a way. On Enceladus, the conditions in the ocean, while extreme, are not beyond the tolerance limits of Earth life. The temperatures are cold, but psychrophilic microbes on Earth survive at similar temperatures. The pressures are high, but barophilic microbes tolerate comparable or even higher pressures. The salinity is within the range many microbes can handle. The pH, while uncertain, is probably slightly alkaline, similar to Earth's seawater, based on the minerals detected in the plumes. The lack of sunlight is irrelevant. Chemosynthetic organisms don't need light. The isolation from the surface doesn't matter. Many deep subsurface microbial communities on Earth have been isolated from the surface for millions of years, living off chemical energy alone. If anything, Enceladus's ocean might be a haven for life, protected beneath miles of ice from the harsh radiation and temperature extremes of space. The continuous tidal heating provides stable energy input. The water-rock interactions generate chemical fuels. The ocean is well mixed by convection, distributing nutrients and preventing stagnation. From what we know, Enceladus's ocean is habitable. Whether it's actually inhabited is a different question, one we won't be able to answer definitively without going there and looking. But the possibility is real, tantalizingly real, and that possibility drives the scientific push to return to Enceladus with a mission specifically designed to search for life. But detecting life on Enceladus presents unique challenges. We cannot assume that life there would look like Earth life, or use the biosignatures, detecting the signs of life. If life exists on Enceladus, how would we detect it? What would be the telltale signs, the biosignatures, that would distinguish biological processes from mere chemistry? These questions occupy researchers around the world as they plan future missions to ocean worlds. A biosignature is any substance, structure, or pattern whose presence indicates the existence of life. On Earth, we have countless biosignatures: oxygen in the atmosphere, produced by photosynthetic organisms; fossil shells and bones preserved in rock; specific ratios of carbon isotopes in organic molecules; the distinctive shapes of cells and microbes visible under a microscope. But detecting life on Enceladus presents unique challenges. We cannot assume that life there would look like Earth life, or use the same biochemistry, or leave the same signs. We need biosignatures that are as general as possible, based on fundamental principles rather than specific details of Earth biology. Scientists have identified several classes of biosignatures that could be detected in Enceladus's plumes. The first class involves the presence and distribution of specific organic molecules. On Earth, living organisms produce amino acids, the building blocks of proteins. There are hundreds of possible amino acids, but Earth life uses only 20 common ones. Moreover, Earth life uses only left-handed, or L-form, amino acids, even though amino acids can exist in both left-handed and right-handed mirror image forms called enantiomers. This preference for left-handed amino acids is called homochirality. It's a biosignature because there's no known abiotic process that produces such a strong preference. Chemical reactions that create amino acids without the involvement of life produce equal amounts of left and right-handed forms, a 50-50 mixture called a racemic mixture. If we detected amino acids in Enceladus's plumes and found that they showed a strong preference for one-handedness, that would be compelling evidence for biology. The challenge is that amino acids break down over time, and their handedness can flip through a process called racemization. We would need to find fresh samples, recently produced, to see a clear biosignature. Fatty acids are another potential biosignature. On Earth, organisms produce fatty acids with specific chain lengths and patterns. Bacterial fatty acids typically have even numbers of carbon atoms, like 14, 16, or 18 carbon fatty acids. This even number preference reflects the way organisms synthesize these molecules, adding 2 carbon units at a time. Abiotic chemistry, in contrast, produces fatty acids with characteristic biological distributions in Enceladus's plumes would suggest biological production. Lipids, the molecules that form cell membranes, provide another line of evidence. Earth organisms use specific lipids with characteristic structures. Archaea and bacteria use different types of lipids, allowing scientists to distinguish between these domains of life based on lipid composition. The presence of intact lipids, especially in patterns resembling cell membranes, would be a strong biosignature. A second class of biosignatures involves patterns in the chemical composition that indicate active metabolism. Living organisms are not in chemical equilibrium with their environment. They take in nutrients, process them, and expel waste products, maintaining themselves far from equilibrium through the continuous expenditure of energy. One way to detect this disequilibrium is through isotope ratios. Carbon, for example, has 2 stable isotopes, carbon-12, the common form, and carbo. Carbon-13, the heavier but rarer form. When organisms metabolize carbon compounds, they preferentially use the lighter carbon-12 because it reacts slightly faster. This results in organic matter from living things having a higher ratio of carbon-12 to carbon-13 than would be expected from purely chemical processes. This carbon isotope fractionation has been used to identify some of the oldest evidence for life on Earth in rocks more than 3.5 billion years old. If we measured the carbon isotopes in organic molecules from Enceladus's plumes and found deviations from the expected ratios, it could indicate biological processing. Similar isotopic signatures exist for other elements. Nitrogen isotopes show fractionation during biological nitrogen fixation and metabolism. Sulfur isotopes are affected by sulfate-reducing bacteria. Hydrogen isotopes vary depending on metabolic pathways. looking for consistent patterns across multiple isotope systems, would provide stronger evidence than relying on a single measurement. A third class of biosignatures involves the detection of molecules that are clearly biological in origin. On Earth, certain molecules are produced only by living things. Chlorophyll, for example, is produced only by photosynthetic organisms. ATP, adenosine triphosphate, is the universal energy currency of life and is found in all cells, but nowhere else in nature. DNA and RNA, the molecules of heredity, are unambiguous biosignatures. No known abiotic process produces long, complex sequences of nucleotides. If we detected nucleic acids in Enceladus's plumes, it would be definitive proof of life. But we shouldn't expect to find DNA or RNA in the plumes, at least not intact. These molecules are fragile and would likely be destroyed during the violent eruption from the ocean through the ice and into space. The same applies to whole cells. While it's possible that intact cells could survive the journey, it's more likely that the would be shattered by the shock of eruption and exposure to vacuum. What we might find instead are cell fragments, pieces of membranes, degraded proteins, individual amino acids or lipids, along with smaller metabolic molecules. Piecing together evidence from these fragments would be like assembling a jigsaw puzzle without the picture on the box. A fourth class of biosignatures involves detecting patterns or structures that suggest life. On Earth, microorganisms often form distinctive morphologies: spheres, rods, spirals, filaments. They may arrange themselves in chains or clusters. Under a microscope, these shapes are instantly recognizable as biological. If we could collect ice grains from Enceladus's plumes and examine them under a microscope, we might see similar structures. The challenge is that many non-biological processes can create shapes that superficially resemble cells. Mineral grains can be spherical. Clay particles can form filaments. We would need to combine morphologic observations with chemical analysis to rule out non-biological explanations. Some proposed future missions to Enceladus would include microscopes capable of imaging individual ice grains at the nanometer scale. Others would use sophisticated mass spectrometers to analyze thousands of molecules simultaneously, creating a detailed chemical fingerprint of the ocean's composition. Still others would employ multiple complementary instruments, each looking for different types of biosignatures to build a comprehensive case. The key principle in astrobiology is that no single measurement is likely to be definitive. Instead, scientists look for convergence of evidence. If multiple independent tests all point toward biology, and if non-biological explanations can be ruled out for each one, then the cumulative case becomes strong. This approach was used to evaluate the famous ALH 84001 meteorite from Mars, found in Antarctica in 1984. The rock, which originated on Mars and was blasted into space by an asteroid impact, contained several features that some scientists argued were evidence of ancient Martian life. The announcement in 1996 that this meteorite might contain evidence of Martian life created enormous excitement and controversy. Over the following years, each piece of evidence was scrutinized intensely. Alternative, non-biological explanations were proposed for most of the features. The scientific consensus today is that while worlds for Enceladus, multiple mission concepts have been proposed. Some would fly repeatedly through the plumes, collecting samples each time and analyzing them with sophisticated instruments. Others would orbit Enceladus and use remote sensing to study the surface and plumes from a distance. Still others propose landing on the surface near the tiger stripes to collect fresher samples that haven't been altered by exposure to space. Each approach has advantages and disadvantages. Flyby missions are less expensive and technically simpler, but they collect samples that have been frozen and exposed to vacuum and radiation, which might degrade biosignatures. Lander missions can collect pristine samples and conduct more detailed analysis, but they're more expensive, riskier, and must operate in the harsh conditions of Enceladus's surface. The ideal mission might combine elements of both: an orbiter to study the global context and multiple landing sites to collect and analyze samples. Such a mission might cost several $billion and take decades to develop and fly. But the scientific payoff, the possibility of discovering life beyond Earth, would justify the investment. NASA's Planetary Science Decadal Survey, a community-driven process that sets priorities for planetary exploration, identified an Enceladus life detection mission called Enceladus Orbalander as the second highest priority large flagship mission for the decade from 2023 to 2032. This mission would orbit Enceladus, fly through the plumes dozens of times to sample them extensively, and then land near the tiger stripes for in-depth surface analysis. The European Space Agency is also considering an Enceladus mission as one of its next large-class science missions. A committee of planetary scientists identified Enceladus as the most compelling target, noting that no space agency has ever landed on this moon despite its enormous potential for astrobiology. Whether the next mission to Enceladus launches in the 2030s or later, the search for biosignatures will be at the heart of its scientific goals. And when that mission analyzes samples from the plumes, the whole world will be watching, hoping for the discovery that would change everything we know about life in the universe. Origin of life in an alien ocean. If life exists on Enceladus, how did it begin? The question of how life originates from non-life, a process called abiogenesis, is one of the deepest mysteries in science. Understanding how life might start in Enceladus's ocean requires us to think about the origin of life on Earth and whether similar processes could occur in very different environments. On Earth, life appeared surprisingly quickly in geological terms. The planet formed about 4.5 billion years ago. For the first few 100 million years, Earth was hellish. Molten rock, constant asteroid bombardment, a toxic atmosphere with no oxygen. But by 3.5 billion years ago, perhaps earlier, microbial life was already established. We know this from fossilized stromatolites, layered structures built by communities of microorganisms, found in rocks of that age. This means life emerged during a relatively narrow window, perhaps as little as a few 100 million years, after Earth became cool enough to have stable liquid water. Either abiogenesis is easier than we think, or Earth got very lucky. Scientists have proposed many theories for how life began on Earth. One of the most influential is the RNA world hypothesis. This theory suggests that before DNA and proteins, early life used RNA molecules that could both store genetic information and catalyze chemical reactions. RNA can do both jobs, though not as efficiently as DNA for storage or proteins for catalysis. Eventually, evolution invented DNA for better information storage and proteins for better catalysis. And RNA became an intermediary, the messenger. The RNA world hypothesis is appealing because it solves the chicken and egg problem. Which came first, nucleic acids to store information or proteins to do the work? In the RNA world, RNA does both, but how did the first RNA molecules form? This remains an open question. Another theory focuses on metabolism first, rather than genetics. This hypothesis suggests that before self-replicating molecules like RNA, there were self-sustaining chemical cycles that could harvest energy from the environment. These proto-metabolic networks might have operated on mineral surfaces at hydrothermal vents, using the chemical energy from water-rock reactions. Certain minerals, like iron-nickel sulfides found at hydrothermal vents, can catalyze organic reactions similar to those in modern metabolisms. These minerals have structures that resemble the active sites of enzymes, surfaces gradually becoming more complex until it could operate independently as free living cells. The hydrothermal vent origin theory has been supported by the discovery that many deep branching lineages of microorganisms, those closest to the root of the tree of life, are thermophiles or hyperthermophiles that thrive at high temperatures. This suggests life may have originated in hot environments, possibly at deep sea vents. Laboratory experiments have shown that many of the building blocks of life can form under conditions similar to those at hydrothermal vents. Amino acids, simple sugars, nucleotide bases, lipids, all can be synthesized abiotically from simple starting materials like hydrogen, carbon dioxide, ammonia, and hydrogen sulfide, given enough energy and the right catalysts. The famous Miller-Urey experiment of 1953 demonstrated that amino acids could form when a mixture of methane, ammonia, water vapor, and hydrogen was subjected to electrical sparks. Simulating lightning. While the specific atmospheric composition they used is now thought to be inaccurate for early Earth, the principle holds. Organic molecules can form spontaneously from simple inorganic precursors under a wide range of conditions. More recent experiments have focused on recreating the chemistry of alkaline hydrothermal vents, a specific type of vent where slightly alkaline, mineral-rich water seeps from the seafloor at moderate temperatures, around 150 to 300 degrees Fahrenheit. These vents, like the Lost City hydrothermal field discovered in 2000, create steep chemical gradients between the alkaline vent fluids and the more acidic ocean water. These gradients, differences in pH, and the concentration of various chemicals can drive the synthesis of organic molecules. The process is similar to how modern cells use proton gradients across membranes to generate ATP. Some researchers believe that the first cells arose from compartment in the porous mineral structures of alkaline vent chimneys, where natural chemical gradients could power protometabolism before biological membranes evolved. Could similar processes occur on Enceladus? The conditions appear favorable. If there are hydrothermal vents on the seafloor, they would create the chemical disequilibrium and energy flow needed for prebiotic chemistry. The continuous supply of hydrogen, carbon dioxide, and other simple molecules would provide raw materials. The circulation of water through the rock would concentrate and transport these materials. The cold temperatures in most of Enceladus's ocean might actually be an advantage for some chemical steps in the origin of life. Cold temperatures slow down reactions. One challenge for life on Enceladus would be the isolation from the surface. On Earth, the surface receives cosmic rays and ultraviolet radiation that can drive chemical reactions and create reactive molecules. The cycling of material between surface and deep ocean on Earth might have been important for the origin of life, bringing together ingredients from different environments. On Enceladus, the thick ice shell blocks most radiation from reaching the ocean, but the plumes provide a mechanism for material to cycle between the ocean and space. Ice particles ejected in the plumes are exposed to radiation, which breaks bonds and creates new compounds. Some particles fall back to the surface. Over time, this material could work its way back down to the ocean through cracks in the ice or through the tiger stripe fractures. Another consideration is time. Life on Earth appeared within perhaps a few 100 million years. Enceladus's ocean might be much younger if it formed only after the Moon was captured into its current orbit and the tidal heating began. Or it might be ancient, dating back to the formation of the solar system 4.5 billion years ago. We don't know. If the ocean is young, maybe only a few 100 million years old, there might not have been enough time for life to arise, even if the conditions are favorable. If the ocean is ancient, life might have had billions of years to emerge and evolve. The origin of life might be rare and difficult, requiring very specific conditions and a great deal of luck. Or it might be relatively easy and inevitable, given liquid water, chemical energy, and enough time. We have only one example, Earth, which makes it hard to know which scenario is correct. This is one reason why searching for life on Enceladus and other ocean worlds is so important. If we find life on Enceladus, and if we can determine that it originated independently from Earth life, rather than being related through panspermia, it would prove this. Abiogenesis can occur multiple times in a single solar system. It would suggest that life is common in the universe, arising wherever conditions permit. If we search thoroughly and find nothing, that would also be informative, though more ambiguous. It might mean that life requires conditions we don't yet understand, or that abiogenesis is incredibly rare. Or it might simply mean that Enceladus's ocean is too young, or that life exists there, but in forms or concentrations we couldn't detect. Scientists have calculated the odds of finding life on Enceladus based on various assumptions. If life is common and arises quickly wherever conditions are right, the chances are high, perhaps 50% or more. If life is rare and requires billions of years to emerge, the chances drop to perhaps a few percent. If life is incredibly rare, a cosmic accident that happened once on Earth through an unlikely series of events, the chances are essentially zero. Nobody knows which estimate is correct. That's why we have to go and look. The only way to answer the question is through observation and experiment. And fortunately, Enceladus offers us the opportunity to conduct that experiment, to test whether life can arise in an alien ocean beneath the ice of a small moon in the outer solar system. The philosophical implications of discovering life on Enceladus would be profound. It would mean we are not alone, that biology is a universal phenomenon, at least within our solar system. It would raise new questions about the diversity of life, the range of environments where it can exist, the biochemical possibilities beyond Earth's DNA protein life. It would also raise practical questions. If life exists on Enceladus, do we have ethical obligations toward it? Should we protect it from contamination by Earth microbes? Should we limit human activities that might disturb or destroy it? Future missions. For now, the mystery remains. Somewhere deep beneath the ice, in the dark waters of Enceladus's ocean, the chemistry of life might be unfolding, or perhaps has already unfolded, creating living things that swim and metabolize and reproduce in ways we can barely imagine. Or perhaps the ocean remains sterile, filled with complex organic chemistry, but not quite crossing the threshold into biology. We won't know until we go there and check. And that is exactly what we plan to do. Designing a life detection mission. Planning a mission to search for life on Enceladus is one of the most exciting and challenging endeavors in space exploration. Let us explore how scientists and engineers are designing spacecraft and instruments that could finally answer the question, are we alone? A life detection mission to Enceladus faces numerous constraints. It must survive the harsh environment of deep space and the intense radiation near Saturn. It must carry enough fuel for a project to 8-year journey from Earth. It must be equipped with instruments sensitive enough to detect biosignatures in tiny samples. And it must do all this within a reasonable budget, ideally less than $5 billion. Several mission concepts have been studied in detail. One of the most comprehensive is the Enceladus Orbolander, recommended by NASA's Planetary Science Decadal Survey as a flagship-class mission. This mission concept includes 2 main phases, an orbital phase lasting about 3 years, followed by a surface phase lasting 2 years. During the orbital phase, the spacecraft would circle Enceladus in an elliptical orbit, passing through the plumes dozens of times. Each plume passage would last only a few minutes, but during that time, instruments would collect ice grains and gas molecules and analyze them immediately on board the spacecraft. The orbiter would carry a suite of advanced instruments, a mass spectrometer similar to but more sensitive than Cassini's would measure the precise masses and compositions of thousands of molecules. This instrument would be able to detect amino acids, fatty acids, lipids, sugars, nucleotide bases, and more complex organic molecules at concentrations of parts per trillion. An ice grain analyzer would capture individual ice grains and examine their composition, looking for signs of cell membrane lipids or other biological molecules trapped in the ice. A microscope would image the grains at nanometer resolution, searching for structures that might indicate cellular origin. A gas chromatograph would separate and identify volatile organic compounds in the plume vapor. This technique can distinguish between different isomers of molecules, including left and right-handed forms of chiral molecules like amino acids. Detecting a preference for one-handedness would be strong evidence for biology. Identify amino acids and other charged molecules, determining their concentrations with high precision. This would allow scientists to look for characteristic biological distributions and patterns. After completing the orbital survey, the spacecraft would descend to the surface and land near one of the tiger stripe fractures, perhaps within a few kilometers of an active jet. The lander would carry a different set of instruments optimized for surface operations. A sample collection system would gather fresh ice from the surface, perhaps by scooping or drilling to depths of several centimeters below the surface where material hasn't been altered by radiation. This pristine sample would be heated and melted, and the meltwater would be analyzed by the lander's instruments. A miniaturized laboratory on the lander would conduct multiple tests on the sample. It would measure the concentrations of organic and inorganic compounds, look for amino acids and their ... handedness, search for fatty acids with biological distributions, analyze carbon and other isotope ratios, and conduct tests specifically designed to detect metabolic activity. One such test might be similar to the labeled release experiment on NASA's Viking landers on Mars in the 1970s. In that experiment, a nutrient solution containing radioactive carbon was added to a soil sample, and the instrument monitored whether radioactive carbon dioxide was released, which would indicate that microorganisms in the soil had metabolized the nutrients. While the Viking results were controversial and ultimately considered inconclusive, the concept remains sound. A similar test on Enceladus might detect metabolically active microorganisms in the ice. Another instrument might be a high-resolution microscope, possibly an atomic force microscope or scanning electron microscope, capable of imaging objects at the scale of individual bacteria, which are typically 1 to 10 micrometers in size. If living or fossil microorganisms are present in the ice, such a microscope might be able to see them directly. The lander would also carry a seismometer to study Enceladus's interior structure and listen for ice quakes or the rumbling of underground water movements. Cameras would provide panoramic views of the landscape, showing the tiger stripes and perhaps active jets in the distance. An instrument to measure the thickness of the ice shell would use radar or electromagnetic sounding to map the ice-ocean boundary. All of this data would be transmitted back to Earth through a relay orbiter or directly using a high-gain antenna. The time delay for signals traveling from Enceladus to Earth is about 80 minutes, the time it takes light to cover the 900 million mile distance. Commands sent from Earth take another 80 minutes to reach Enceladus. This means the spacecraft must be highly autonomous, capable of making decisions on its own during critical operations, like landing or plume sampling. The spacecraft would be powered by a nuclear generator, similar to those used on Cassini, the Mars Curiosity and Perseverance rovers, and the New Horizons mission to Pluto. Solar panels are impractical at Saturn's distance because sunlight is too weak. A single advanced radioisotope thermoelectric generator, using the decay heat from plutonium-238, could provide about 300 watts of electrical power continuously for decades. Launch would likely use a SpaceX Falcon Heavy rocket, or NASA's Space Launch System. The spacecraft would fly a trajectory similar to Cassini's, using gravity assists at Earth, Venus, or Jupiter to reach Saturn. The total trip time would be 7 to 8.5 years, depending on the specific trajectory. Once at Saturn, the spacecraft would use chemical propulsion to slow down and enter orbit around the planet, then gradually lower its orbit over months or years until it rendezvous with Enceladus. Fuel for these maneuvers would account for a significant fraction of the spacecraft's launch mass. Landing on Enceladus presents unique challenges. The surface gravity is extremely weak, only about 1% of Earth's. This means the lander doesn't need to slow down much, but it also means it won't stick to the surface very well. The lander might need anchoring harpoons or ice screws to prevent it from bouncing or sliding. The surface is probably covered in fresh, snow-like ice, which might be soft and fluffy, or could have a hard crust with soft material beneath. The lander's feet need to distribute its weight to avoid sinking into the snow. And the landing site must be chosen carefully to avoid steep slopes or rough terrain. The low gravity also affects the plume structure. The jets of material ejected from the tiger stripes don't fall back quickly. They arc gracefully into space, reaching heights of hundreds of miles before the particles eventually settle back to the surface or escape Enceladus entirely. An orbiter flying through these plumes would experience them as a diffuse mist rather than a solid wall. Temperature control is critical. Surface temperatures of -200 degrees Fahrenheit will freeze any exposed electronics within minutes. The spacecraft must have robust thermal insulation and heaters to keep critical components warm. But the nuclear generator produces heat continuously, so disposing of excess heat in the vacuum of space is also a concern. The spacecraft would use radiators to radiate away heat, balanced with heaters and insulation to maintain components within their operating temperature ranges. Radiation from Saturn's magnetosphere is less intense at Enceladus than at Europa, because Enceladus orbits farther from its host planet. But it's still a concern. The spacecraft electronics would need some radiation shielding, and mission planners would need to account for gradual degradation of components over the mission's lifetime. Planetary protection is another critical consideration. Earth is teeming with hardy microorganisms that can survive extreme conditions. If any of these hitchhikers made it to Enceladus and contaminated the ocean, they could potentially compromise the search for native life or even threaten any ecosystem that exists there. To prevent this, the spacecraft would be assembled in clean rooms and sterilized through a combination of heat treatment, ultraviolet radiation, and chemical disinfection. For a mission to an ocean world like Enceladus, NASA's planetary protection guidelines would require very thorough sterilization, much more stringent than for missions to less sensitive targets. Even with these precautions, there's always a small risk. The lander, operating on the surface near active jets, could potentially contaminate the ocean through the fractures. Mission designs try to minimize this risk by landing at a safe distance from the most active jets and by ensuring the lander won't leak or shed materials. The mission would cost an estimated $4 to $5 billion, comparable to flagship missions like Cassini. Development would take about 10 to 12 years from approval to launch, including the 7 to 8 year cruise to Saturn. We're looking at 2 decades from the start of the project to the first results. This is why decisions about which missions to fly are so consequential. With limited budgets and long timelines, space agencies can pursue only a few large missions per decade. Choosing to fly to Enceladus means not flying to other equally interesting targets, at least not in the near term. But the potential payoff is extraordinary. A single positive detection of life on Enceladus would be one of the greatest discoveries in the history of science, comparable to Galileo's observations of Jupiter's moons or Darwin's theory of evolution. It would fundamentally change how we view our place in the universe. Even a null result, a thorough search that finds no signs of life, would be scientifically valuable. It would tell us that either life doesn't exist on Enceladus, or that it's rare enough or different enough that we couldn't detect it with our methods. That would inform future searches and refine our understanding of what conditions are necessary for life. As of 2025, autonomous navigation and landing are improving. Concepts for sterilization and planetary protection are being refined, and our knowledge of Enceladus continues to grow as researchers analyze Cassini's data. New discoveries are still being published years after the mission ended, each one adding to our understanding and helping to plan what questions the next mission should address. The search for life on Enceladus is a marathon, not a sprint. But with each step, we get closer to the moment when a spacecraft will land on that distant moon, melt a sample of ice, and test it for the signs of life. When that moment comes, the whole world will hold its breath, waiting to learn whether we are alone, or whether life, in its infinite creativity, has found a way to exist in the cold, dark ocean beneath the ice of Saturn's moon. The broader search. As we near the end of our journey tonight, let us step back and consider the broader context of the search for life in our solar system and beyond. Enceladus is one piece of a much larger puzzle, a puzzle that humanity is only beginning to solve. The past few decades have brought a revolution in astrobiology. When Cassini launched in 1997, we knew of no planets beyond our solar system. Today, We've discovered more than 5,000 exoplanets, worlds orbiting distant stars. Statistical analyses suggest there could be billions of potentially habitable planets just in our Milky Way galaxy. But distances in space are vast. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. Interstellar travel, at least with current technology, remains firmly in the realm of science fiction. This makes our own solar system incredibly precious for the search for life. These are worlds we can reach, at least with robotic spacecraft. Timescales of years rather than millennia. We can study them in detail, land on them, drill into them, and search directly for life. Mars has been the primary focus of astrobiology for decades. NASA's Perseverance rover, which landed in February 2021, is actively searching for signs of ancient microbial life and collecting rock samples that a future mission will retrieve and return to Earth for detailed analysis. Venus, Earth's other neighbor, is a hellish world. But the detection of phosphine gas in its atmosphere raised the tantalizing possibility that microbes might exist in the planet's clouds, where temperatures are more moderate. The icy moons of the outer solar system, Europa, Enceladus, Titan, and possibly others, represent a different category of potentially habitable worlds. Unlike Mars or Venus, which depend on their star for warmth, these moons are heated from within by tidal forces. They could remain habitable for billions of years, regardless of CHA. In the sun's luminosity, this has profound implications for the search for life in the universe. If tidal heating can create habitable environments inside moons, then potentially habitable conditions might exist in many places where we wouldn't normally look. This expands the habitable zone dramatically, potentially making life much more common in the universe than we previously thought. The concept of habitability itself has evolved. Traditionally, we defined the habitable zone as the region around a star where temperatures allow liquid water on a planet's surface. But Enceladus and Europa have taught us that liquid water can exist beneath ice shells far from any star. Titan has shown us that interesting chemistry and possibly even exotic forms of life might exist in liquids other than water. We now recognize that habitability is not a binary yes or no question, but a spectrum. This raises the question, how do we search for life we might not recognize? All our biosignature definition are based on Earth life. Some scientists advocate for a more general approach to life detection, looking not for specific molecules, but for patterns that indicate complexity, organization, and disequilibrium. The search for life beyond Earth is entering a new phase. For the first time in history, we have the technology to seriously address the question. Within the next few decades, we may have our answer. We may discover that life is common, arising independently in multiple locations, even within our own solar system. Or we may find that despite extensive searching, Earth appears to be unique, at least in our cosmic neighborhood. Either answer would be profound. If we find life on Enceladus, or Mars, or Europa, and if we can verify that it originated independently, it would prove that abiogenesis can occur multiple times. Life would no longer be a cosmic accident, but a cosmic imperative, arising wherever conditions permit. We would know thoroughly and find nothing. It would be a lonelier, but equally important result. It would tell us that life is rare, that Earth is special, and that we have a profound responsibility to protect and preserve the life here. Either way, the search itself ennobles us. It represents humanity at its best, curious ambitious, cooperative, looking beyond our immediate needs to ask the deepest questions about existence. When you look at Enceladus, a tiny moon 800 million miles away, smaller than Arizona, and realize that beneath its frozen surface might be an ocean teeming with alien life, it changes how you see the universe. You realize that life, if it exists, is probably not confined to planets like Earth, but might flourish in the most unlikely places. As you drift off to sleep tonight, think about that ocean beneath the ice. Imagine the jets erupting from the tiger stripes, carrying samples of that alien sea into space. Imagine a future mission, landing near those jets, collecting samples and discovering the first proof of life beyond Earth. Imagine how that discovery would unite humanity in the shared understanding that we are part of something much larger than ourselves. Somewhere in the darkness, 900 million miles away, Enceladus continues its eternal orbit around Saturn. The plumes continue to erupt. The ocean continues to exist, perhaps harboring life that has evolved in complete isolation from Earth. And when that discovery happens, if it happens, we will remember this moment, this time when Enceladus was still a mystery, when the question of whether we are alone remained unanswered, when the future was full of possibility and wonder. Sleep well, knowing that out there in the vast cosmos, on a small moon circling a ringed giant, a hidden ocean waits to reveal its secret.
Welcome to Echo of Dreamlab, a place where curiosity meets calm. Here we drift slowly through the quiet glow of night, exploring the soft, hidden wonders of science and rest. So, settle in, breathe gently, and let your mind wander as we journey together into the science of dreams. As we enter the final chapter of our journey tonight, let us look forward to what comes next. The story of Enceladus is far from over. In fact, the most exciting chapters may still be ahead of us. Plans are being made, technologies are being developed, and spacecraft are being designed that will one day return to that tiny moon and search in earnest for signs of life. The most comprehensive mission concept currently under serious consideration is the Enceladus Orbilander. This flagship mission was designated as the second highest priority for large planetary missions in NASA's Planetary Science Decadal Survey for 2023 through 2032. Only a mission to Uranus, which has never been thoroughly explored beyond Voyager 2's brief flyby, ranks higher in the recommended priorities. The Enceladus Orbilander represents more than a decade of careful study by scientists and engineers at the Johns Hopkins University Apple Laboratory. Working with experts from around the world, the mission concept was led by Shannon McKenzie, a planetary scientist whose team spent years analyzing what kind of mission would best address the fundamental questions about Enceladus while remaining technically feasible and affordable. The baseline design calls for a single spacecraft that serves as both an orbiter and a lander. This combined approach is possible because of Enceladus's tiny size and weak gravity. On a larger world like Mars or Europa, landing requires tremendous amounts of fuel to slow down from orbital speeds. But on Enceladus, the gravity is so weak that the delta V, the change in velocity needed to land, is almost negligible. A spacecraft in orbit around Enceladus could land using very little propellant, making the combined orbiter-lander architecture practical. The mission would launch in the late 2030s, most likely aboard either NASA's Space Launch Site, a SpaceX Falcon Heavy rocket. Both vehicles are capable of sending the roughly 5-ton spacecraft on its way towards Saturn. The journey would take approximately 7.5 years. following a trajectory that might include gravity assists from Venus, Earth, or Jupiter to build up the necessary velocity. Arrival at Saturn would occur in the mid-2040s, more than 20 years from now. But given the complexity of the mission and the current constraints on NASA's budget, this timeline represents an optimistic scenario, using gravity assists from other moons to lower its orbit and approach Enceladus. This Saturn tour phase would allow preliminary observations of the Saturn system while efficiently changing the spacecraft's trajectory to match Enceladus's orbit. The orbital phase of the mission would last approximately 1.5 years. During this time, the spacecraft would orbit Enceladus in an elliptical path with a period of about 12 hours. The closest approach on each orbit would bring the spacecraft directly over the South Polar Tiger Stripes at altitudes as low as 30 to 50 kilometers, passing through the densest parts of the plumes. Each plume passage would last only minutes, but in that brief time, the spacecraft's instruments would collect and analyze samples of ice grains and vapor. Unlike Cassini, which had to balance observations of Enceladus with many other targets throughout the Saturn system, the Orbilander would be dedicated solely to studying this one moon. It would accumulate far more data in 18 months than Cassini collected during its entire 13-year mission. The spacecraft would carry a suite of 5 instruments, collectively called the Life Detection Suite. These instruments represent significant advances over what flew on Cassini. They are more sensitive, capable of detecting much smaller concentrations of organic molecules. They can distinguish between different isomers of the same molecule, crucial for identifying biological signatures, like the handedness of amino acids, and they can detect larger, more complex molecules that Cassini's instruments weren't designed to measure. The first instrument is an advanced mass spectrometer, similar in principle to Cassini's ion and neutral mass spectrometer, but with far greater sensitivity and resolution. It can identify thousands of different molecules simultaneously, measuring their masses with precision sufficient to distinguish between mole. Differ by less than 1 atomic mass unit. The second instrument is an organic analyzer, specifically designed to search for amino acids, the building blocks of proteins. It would separate amino acids using a technique called capillary electrophoresis, then measure whether they show the left-handed preference characteristic of Earth life. Detection of homochiral amino acids in the plumes would be strong evidence for biological processes. The third instrument is a lipid analyzer. Lipids are the molecules that form cell membranes. This instrument would look for fatty acids and other lipid molecules with the characteristic structures and chain lengths produced by living organisms. It would also search for intact lipid vesicles, the microscopic bubbles that could represent fragments of cell membranes. The fourth instrument is a microscope, capable of imaging individual ice grains at nanometer resolution. Some proposed versions would use atomic force electron microscopy techniques to resolve structures smaller than a single bacterium. If intact cells or even cell fragments were present in the plumes, this instrument might be able to see them directly. The fifth instrument is a metabolic analyzer. This device would conduct experiments on melted samples of plume ice, looking for chemical evidence of active metabolism. It might add nutrients labeled with radioactive carbon and monitor whether any organisms consume them and release carbon dioxide. Similar to the labeled release experiment on the Viking Mars landers, but with much greater sensitivity. Throughout the orbital phase, cameras and other remote sensing instruments would map the surface in detail, identifying potential landing sites near the Tiger Stripes. The spacecraft would also measure Enceladus's gravity field more precisely than Cassini did, refining our understanding of the ocean's depth and the ice shell's thickness. After completing the orbital survey, the Orbalander would begin its descent to the surface. Using terrain-relative navigation, similar to the system that guided NASA's OSIRIS-REx spacecraft to asteroid Bennu, the lander would autonomously identify and avoid hazards during the final approach. This capability is essential because mission controllers on Earth, 80 light minutes away, cannot react quickly enough to guide the landing in real time. The landing site would be chosen to maximize scientific return while minimizing risk. Ideally, it would be within a few kilometers of one of the active jets, close enough to collect fresh material falling from the plumes, but far enough away to avoid steep slopes or rough terrain. The surface in the South Polar region is young and probably relatively smooth, making it suitable for landing. Because Enceladus's gravity is only about 1% of Earth's, landing doesn't require powerful braking engines. The spacecraft will descend slowly, perhaps at speeds of just a few meters per second, and touch down gently on shock-absorbing legs. Anchoring systems, possibly harpoons or ice screws, would prevent the lander from bouncing or being dislodged by any seismic activity. The surface mission would last at least 2 years, possibly longer if the spacecraft remains functional and its nuclear power source continues to provide electricity. During this time, the lander would conduct an intensive campaign of sample collection and analysis. A robotic arm or scoop would gather surface ice from multiple locations around the landing site. This ice, which has settled from the plumes over time, represents ocean material that has been frozen and possibly altered by exposure to vacuum and radiation. But it hasn't been diluted or contaminated by traveling through space, so it should contain higher concentrations of organic molecules than the samples collected in orbit. The ice would be heated and a clean sample processing system, then analyzed by miniaturized versions of the life detection suite instruments. Multiple samples would be tested to account for spatial variability. If the lander is fortunate enough to be near an active vent, it might even collect material falling directly from a jet, providing the freshest possible samples. In addition to life detection experiments, the lander would deploy a seismometer to listen for Enceladus quakes and the rumbling of water moving beneath the ice. It would measure heat flow from the surface, helping to constrain models of the interior temperature and the thickness of the ice shell. Cameras would provide panoramic views of the alien landscape, potentially capturing images of the plumes erupting in the distance. All of this data would be transmitted back to Earth through a relay system, either via a separate orbiter left in place around Enceladus, or directly using a high-gain antenna when Earth is V. Time delay means that scientists on Earth couldn't control experiments in real time. The spacecraft would need significant autonomy to make decisions, prioritize observations, and respond to unexpected conditions. The estimated cost for the Enceladus Orbalander mission is approximately $4.9 billion in 2025 dollars. This is comparable to other flagship missions like Cassini, which cost about $3.3 billion, or the Mars 2020 Perseverance rover at $2.7 billion, for the potential payoff of discovering life beyond Earth. Many scientists argue this is an entirely reasonable investment, but the mission faces stiff competition for limited funding. NASA's planetary science budget is constrained, and multiple worthy missions are competing for approval. A Uranus mission has higher priority. Mars sample return, if it proceeds, will consume billions of dollars. The Europa Clipper mission, launched in October 2024, cost over $5 billion, reducing available funds for future flagships. Even if the Enceladus Orbolander is approved in the late 2020s, it wouldn't launch until the late 2030s at the earliest. Add 7 years for the cruise to Saturn, and another year for the Saturn tour, and we're looking at the late 2040s before the mission begins its science operations. That's still more than 2 decades away. For scientists who have dedicated their careers to studying Enceladus, this timeline is frustrating. Many who worked on Cassini won't live to see the next mission arrive. Graduate students beginning their studies today will be established researchers in mid-career, before the Orbolander results come back. But this is the reality of deep space exploration. These missions take decades to plan and execute. The patience required is immense, yet the potential reward, the possibility of answering whether we are alone in the universe, makes the wait worthwhile. Alternative approaches, faster, cheaper options. While the Enceladus Orbolander represents the most comprehensive approach to exploring Enceladus, it's not the only option. Several alternative mission concepts have been proposed that could reach Enceladus sooner and at lower cost. Though with reduced science capabilities, one such concept is the Enceladus Life Finder, or ELF, proposed by Jonathan Lunine and colleagues at Cornell University. ELF was submitted to NASA's new Frontiers program in 2017, competing for a mission slot with a budget cap of around $1 billion, much less than a flagship mission. The ELF mission would not orbit Enceladus or land on it. Instead, it would orbit Saturn and make multiple close flybys of Enceladus of about 3 years, flying through the plumes 8 to 10 times. Each flyby would collect and analyze samples using 2 highly sensitive mass spectrometers. The key advantage of ELF is its relative simplicity and lower cost. By not entering orbit around Enceladus or landing, the mission requires less fuel and can use solar panels for power, instead of expensive radioisotope generators. The spacecraft could be smaller and lighter, reducing launch costs. However, ELF would collect less data than Orbolander, with only 8 to 10 plume passages compared to potentially dozens from orbit and continuous sampling on the surface. ELF would have fewer opportunities to detect rare or variable biosignatures. And without a lander, it couldn't study the surface directly or deploy seismic instruments. ELF was not selected for the new Frontiers 4 competition, which chose the Dragonfly mission to Saturn's moon Titan instead. But and could be proposed again in future NASA mission selections. Another interesting proposal is the Tiger mission, which stands for Thermal Investigation of Geothermal Regions of Enceladus. Presented at the 2025 Lunar and Planetary Science Conference, Tiger envisions a lander mission that would focus on measuring heat flow and thermal properties near the Tiger stripes. Tiger would not carry the full complement of life detection instruments. Instead, it would concentrate on understanding the geology and geophysics of Enceladus, measuring how heat flows from the interior, mapping temperature variations across the surface, and using ground-penetrating radar to probe the structure of the ice shell. This more focused approach could potentially be done at lower cost than Orbolander, perhaps $2 to $3 billion, and by concentrating on geophysical measurements rather than direct life. Tiger would complement rather than duplicate Orbolander's science goals. Some scientists have proposed even more ambitious concepts. One idea is to send a small submarine or autonomous underwater vehicle into Enceladus's ocean, called SWIM, for sensing with independent micro-swimmers. This concept envisions deploying dozens of tiny robotic devices that could disperse throughout the ocean, measuring temperature, salinity, pH, and chemical composition at multiple locations. The challenge, of course, is getting the swimmers into the ocean. They would need to be delivered through one of the tiger stripe fractures, perhaps lowered on a tether, or released to free fall through the fracture and into the water. The ice could be several kilometers thick, even at the thin spots, making this extraordinarily difficult. Another concept proposes using a melter probe, similar to devices tested in Antarctica, to penetrate ice. The probe would use heat from a nuclear source to melt its way through the ice, slowly descending over months or years until it reaches the ocean. Once there, it would deploy sensors to study the ocean directly. This approach has been studied extensively for Europa, where the ice is even thicker and technical challenges are formidable. The probe would need kilometers of communications cable to stay in contact with a surface relay station. It would need to navigate around boulders or dense layers in the ice that might block its progress. And it would need to avoid getting stuck in refrozen ice behind it. For Enceladus, with its thinner ice at the South Pole and the presence of the fractures, melter probes might be more practical than for Europa. But the technology is still decades away from being ready for deployment. Perhaps the most audacious proposal comes from the Breakthrough Initiatives, a privately funded program founded by billionaire Yuri Milner. Enceladus aims to develop a relatively low-cost mission that could fly to Enceladus and search for life, using private funding rather than government support. The appeal of this approach is speed and flexibility. Private missions aren't bound by NASA's budget cycles and mission selection processes. They can move faster, take more risks, and focus solely on the specific goal of life detection, without having to satisfy the broader scientific community's diverse priorities. Critics point out that past private deep space missions have struggled with technical challenges and funding constraints. SpaceIL's Beresheet lunar lander crashed. iSpace's Hakuto R lander also crashed. Deep space missions to the outer solar system are far more complex and expensive than lunar missions. A mission to Enceladus faces a minimum cost of hundreds of millions of dollars, even for the simplest design, and likely well over $1 billion for a capable science payload. Still, the Enceladus concept has attracted serious attention. Christopher McKay, a NASA planetary scientist and expert on astrobiology, has compared it to the great exploration missions of the past: Magellan's circumnavigation of the globe, Byrd's polar expeditions. If successful, it would indeed represent a paradigm shift in how we explore the solar system, demonstrating that private entities can conduct scientifically valuable missions to the outer planets. International cooperation offers another path forward. The European Space Agency, ESA, has expressed strong interest in a mission to Enceladus. In discussions leading up to ESA's large class mission selection for the 2030s and 2040s, Enceladus was identified as one of the most compelling targets. A joint NASA-ESA mission could combine the resources and expertise of both agencies, potentially enabling a more ambitious mission than either could afford alone. Past collabo, like Cassini-Huygens, where NASA provided the orbiter and ESA provided the Titan lander, have been highly successful. China has also shown interest in Enceladus. As part of its rapidly expanding deep space program, China has proposed missions to Jupiter and Neptune and is studying the feasibility of a Saturn mission. Chinese scientists from the Deep Space Exploration Laboratory and the Shanghai Institute of Satellite Engineering published a paper in 2025 outlining a potential Enceladus mission that would include both an orbiter and a lander. The Chinese concept calls for using radioisotope thermoelectric generators for power, advanced trajectory planning to minimize fuel requirements, and in situ resource utilization techniques. One particularly intriguing element of their proposal is a drilling robot that could penetrate beneath the surface to collect subsurface samples less affected by radiation. If multiple nations or agencies send Enceladus over the coming decades, we could see an era of intensive exploration similar to what occurred with Mars in the 2000s and 2010s. Multiple spacecraft, each with different capabilities and scientific objectives, working together to paint a comprehensive picture of this fascinating moon. The diversity of mission concepts, from simple flybys to ambitious landers and even submarines, reflects both the enormous scientific interest in Enceladus and the uncertainty about the best approach. We won't know which strategy is optimal until missions fly, and we learn more about the conditions at Enceladus, the behavior of the plumes, and the nature of the surface. What's certain is that we will return to Enceladus. The scientific case is too compelling, the potential discovery too important to ignore. Whether it's NASA's Orbalander, ESA's contribution, China's mission, a private endeavor, or all of the above, spacecraft will fly through plumes again, land near those tiger stripes, and search for signs of life in the samples they collect. The question is not if, but when. And for those of us alive today, watching these plans develop, the wait feels both agonizingly long and thrillingly imminent. Technologies for the future. Sending a life detection mission to Enceladus requires technologies that, in some cases, don't yet exist in the forms needed. Let us explore the innovations being developed that will make future missions possible. One of the biggest challenges is power. At Saturn's distance from the Sun, solar panels are impractical for most mission architectures. The sunlight is too weak, only about 1% of the intensity at Earth. To generate enough power using solar panels, you would need enormous arrays, too large and heavy to be practical for most deep space missions. Cassini used radioisotope thermoelectric generators, RTGs, which convert heat from the radioactive decay of plutonium-238 into electricity. These devices are highly reliable, providing steady power for decades without moving parts or degradation. But they're also expensive and difficult to produce. The United States supply of plutonium-238 was nearly exhausted by the 2000s, as no more was being manufactured after the end of the Cold War. Efforts to restart production have been partially successful, but availability remains limited. Each RTG requires several kilograms of plutonium-238, which takes years to produce in nuclear reactors. NASA is developing next-generation power sources that could supplement or replace RTGs. One concept is the EMMR-TEG, the Enhanced Multi-Mission Radioisotope Thermoelectric Generator, which uses the same plutonium fuel, but with more efficient conversion of heat to electricity, producing more power per kilogram of fuel. Another approach is the Stirling Radioisotope Generator, which uses a Stirling engine, a MEM, mechanical device with moving parts to convert heat to electricity more efficiently than solid-state thermoelectrics. These generators could provide 2 to 4 times as much power for the same amount of plutonium. But the moving parts might wear out over time, a concern for missions lasting decades. Fission reactors represent another possibility. NASA has developed and tested small nuclear reactors called kilopower units, designed to provide up to 10 kilowatts of electrical power using uranium fuel. These reactors are much more powerful than RTGs and don't require plutonium-238. A reactor-powered spacecraft could support more instruments, more data transmission, active heating to keep components warm, and potentially electric propulsion systems for faster transit times. But reactors are also more complex, heavier, and have never been used on a planetary mission. So considerable development would be needed. Another critical technology is autonomous navigation. The time delay for signals between Earth and Enceladus is about 80 minutes one way. This means mission controllers cannot pilot the spacecraft in real time during critical operations like landing or close plume flybys. The spacecraft must be able to make decisions on its own. During descent to the surface, it needs to identify hazards like boulders, steep slopes, or crevices, and adjust its trajectory to avoid them. This terrain relative navigation requires sophisticated computer vision algorithms, 3D mapping systems, and decision-making software. NASA's recent missions have made great strides in this technology. The Mars 2020 Perseverance rover used terrain relative navigation to land safely in Jezero crater, a site with numerous hazards that would have been too risky for earlier missions. OSIRIS-REx used similar systems to navigate around asteroid Bennu. The challenges are somewhat different. The low gravity means the spacecraft descends slowly, providing more time to assess the terrain and react. But the extreme cold, the unfamiliar surface properties, and the need to avoid contaminating the environment all add complexity. Sample handling and analysis present their own challenges. The instruments must be extraordinarily sensitive to detect biosignatures at very low concentrations, perhaps comparable to or lower than the density of microbes in Earth's most oligotrophic, nutrient-poor waters. Advances in miniaturized mass spectrometry are crucial. Modern mass spectrometers can detect individual molecules and measure their masses with extreme precision. They can separate complex mixtures into thousands of distinct components and quantify each one. Microfluidic devices, tiny laboratories on a chip that manipulate fluids at the microliter scale, allow sophisticated chemical processing with minimal sample size. Wait, these devices can mix reagents, incubate samples, conduct chemical reactions, and measure the products, all within channels narrower than a human hair. Capillary electrophoresis, gas chromatography, and liquid chromatography techniques can separate and identify organic molecules based on their physical and chemical properties. When coupled with mass spectrometry, these methods provide powerful tools for detecting and characterizing potential biosignatures. But perhaps the most important technology is computational, the algorithms and databases that will interpret the data and search for patterns indicative of life. Machine learning and artificial intelligence are increasingly being applied to astrobiology, trained on vast databases of organic molecules from birth life, abiotic chemical reactions, and synthetic pathways. These systems can recognize subtle patterns that human scientists might miss. They can distinguish between biological and non-distributions of molecules, identify unexpected compounds that don't fit known abiotic chemistry, and even suggest metabolic pathways that could produce the observed molecules. However, AI-based life detection also carries risks. If the training data is biased toward Earth life, the systems might miss exotic forms of life that use different biochemistry. There's a danger of false positives, where the AI identifies something as biological when it's actually an unusual but non-biological chemical pattern. Scientists are working to make these systems more robust and general, training them on the widest possible range of scenarios. But ultimately, any claimed detection of life will require human judgment and extensive peer review. The decision about whether we've truly found life will not be made by a machine, no matter how sophisticated, but by the collective wisdom of the scientific community, evaluating all available evidence. Contamination prevention is another technology challenge. We must ensure that we don't carry Earth microbes to Enceladus and potentially contaminate its ocean. This requires sterilization techniques that can eliminate all viable organisms without damaging sensitive instruments. Traditional sterilization methods, like autoclaving, heating components to high temperatures, can damage electronics and optical systems. Dry heat sterilization, exposure to temperatures around 320 degrees Fahrenheit for extended periods, is more compatible with spacecraft components, but still stresses some materials. Alternative approaches include sterilization with hydrogen peroxide vapor, ethylene oxide gas, or high-energy radiation. Each method has advantages and disadvantages, and mission designers must balance sterility requirements against technical constraints and costs. Planetary protection protocols also require bioassays to verify that sterilization was done. Samples are taken from spacecraft surfaces and cultured to detect any surviving microbes. The acceptable bioload, the number of viable spores per square meter, is extremely low for missions to ocean worlds like Enceladus. Some scientists have proposed even more stringent requirements, arguing that we should send no landers to Enceladus or Europa until we can guarantee absolute sterility, effectively zero viable organisms. Others argue that this standard is impractical and would delay exploration indefinitely. The debate continues within the planetary protection community. Finally, there's the technology of patience. These missions take so long to develop and execute that maintaining institutional knowledge and continuity is itself a technical challenge. Engineers and scientists work on projects that may not fly for 20 years. Young team members must be trained to replace retiring veterans. Software must be maintained and updated over decades. Suppliers available to produce spare parts long after initial manufacturing. Managing these long timescales requires careful planning, documentation, and institutional commitment. It's one of the less glamorous, but absolutely essential aspects of deep space exploration. All of these technologies, from power systems to instruments to contamination prevention, are advancing steadily. With each Mars rover, each asteroid mission, each technology demonstration, we get closer to being able to send a capable mission to Enceladus. The pieces are coming together. The capability is emerging. The mission, when it finally flies, will represent the culmination of decades of technological development and the dedicated work of thousands of people. What we might find. Let us engage in a thought experiment now. Imagine that it is the year 2048. The Enceladus orbital lander has been on the surface for 6 months. Data has been back to Earth, and the science team has been analyzing it with increasing excitement. Today, they are holding a press conference to announce their findings. What might they say? One possibility is that they found nothing. No amino acids with biological distributions. No lipids resembling cell membranes. No isotopic signatures of metabolic fractionation. No structures resembling cells in the microscope images. All the biosignature tests came back negative or ambiguous. This would be disappointing, certainly, but it would also be scientifically valuable. It would tell us that either Enceladus's ocean is sterile, or that life there is so rare or so different that our instruments couldn't detect it with the sampling we did. A null result wouldn't close the book on Enceladus. Scientists would argue that we need to sample more locations, dig deeper beneath the surface, look for different types of biosignatures. Future missions propose to address these limitations, but it would reduce confidence in the habitability of ocean worlds. If Enceladus, with its chemical energy, its water-rock interactions, its abundant organic chemistry, doesn't harbor life, then perhaps life is rarer than we hoped. Perhaps the origin of life requires conditions we don't yet understand. A second possibility is an ambiguous result. Perhaps the mission detected amino acids with a slight preference for one-handedness. Suggestive but not definitive. Perhaps isotopic ratios showed small deviations that could be biological, or could be explained by unusual chemical processes. Perhaps the microscope images showed a few structures that looked cell-like, but could also be mineral grains. This scenario would spark intense scientific debate. Some researchers would interpret the data as evidence for life. Others would argue for non-biological explanations. There would be calls for follow-up missions to collect more data and resolve the ambiguities. In many ways, this would be the most frustrating outcome. Not a clear answer either way, but tantalizing hints that require decades more work to sort out. Yet this is how science often proceeds, not with dramatic revelations, but with gradual accumulation of evidence, slowly building toward a consensus. The third possibility is a positive detection, clear, unambiguous biosignatures that could not reasonably be produced by abiotic chemistry. Multiple independent lines of evidence, all pointing in the same direction. Imagine the science team presenting the data. Amino acids showing 95% homochirality, all left-handed, just like Earth life. Fatty acids with even-numbered carbon chains, the signature of biological synthesis. Lipid vesicles visible under the microscope. Perfectly spherical structures with the size and properties of cell membranes. Isotopic ratios of carbon and nitrogen, showing the characteristic fractionation of metabolic processes. And perhaps, most excitingly, positive results from the metabolic activity tests. Samples of melted plume ice, exposed to radioactive nutrients, producing labeled carbon dioxide at rates that can only be explained by living organisms consuming the nutrients. The discovery would be announced carefully. The team would present each piece of evidence systematically, explaining why biological interpretations are strongly favored over non-biological alternatives. They would acknowledge remaining uncertainties and call for peer review and additional observations. But the cumulative case would be compelling. The reaction would be extraordinary. The news would dominate media worldwide. Philosophers and theologians would debate the implications for humanity's place in the world. Science fiction writers would imagine what Enceladian life might be like. Children would grow up knowing that Earth is not the only living world. Scientists would immediately begin planning follow-up missions. What do these organisms look like? How do they metabolize? What is their genetic system? Are they related to Earth life, perhaps through panspermia? Or did they originate independently? If independently, what does their biochemistry tell us about alternative forms of life? The discovery would transform astrobiology from a theoretical field into an experimental science. We would have two examples of life to compare, Earth and Enceladus. From two data points, we could begin to extract general principles. What features are universal to all life? What aspects are contingent on local conditions? If Enceladian life used DNA or something very similar, it might suggest that this molecule is uniquely suited to store genetic information, that convergent evolution. It independently. If it used something completely different, it would expand our understanding of what's possible in biochemistry. Perhaps the most profound implication would be for the prevalence of life in the universe. If life arose independently twice in one solar system, it strongly suggests that life is common wherever conditions are suitable. With billions of potentially habitable planets and moons in the galaxy, the universe would likely be filled with living worlds. We might not be alone. In fact, we might be surrounded by life, on worlds both nearby and inconceivably distant. The cosmos would be not a dead expanse punctuated by rare oases of life, but a living universe, teeming with organisms adapting to every available niche. Of course, there's a fourth possibility, one rarely discussed but worth considering. Perhaps we find something utterly unexpected, not life as we know it, but some phenomenon we can't explain, something that understanding of chemistry or physics or biology. Perhaps the plume samples contain molecules that shouldn't exist, that violate our understanding of chemical thermodynamics. Perhaps we detect energy signatures suggesting reactions that don't fit any known metabolic pathway. Perhaps the isotopic ratios make no sense according to our models of how elements are processed by biological or geological systems. In the history of science, unexpected discoveries have often led to the greatest revolutions in understanding. Radioactivity was unexpected. Cosmic microwave background radiation was unexpected. Dark energy was unexpected. Each discovery opened new vistas and forced scientists to rethink fundamental assumptions. An unexpected finding at Enceladus could do the same. It might reveal new chemistry, new physics, new principles of self-organization that we've never encountered on Earth. It might teach us that the universe is stranger and more wonderful than we cannot help but affect how we see ourselves and our place in the cosmos. Even a null result, the determination that Enceladus is sterile, would reshape our understanding of life's rarity and preciousness. And so we wait, we plan, we develop the technologies, we train the scientists and engineers who will design and operate these missions. We allocate the resources, knowing that the investment now may not pay dividends for decades. We commit to the search, not for immediate gratification, but because the question is too important to ignore. Are we alone? Is Earth's biosphere unique, or is life a cosmic commonplace? The answer lies waiting for us, beneath the ice of a small moon circling Saturn, 900 million miles away. And one day, perhaps within the lifetimes of children alive today, we will retrieve that answer and know the truth. Philosophical implications. As we near the end of our journey, let us step back from the details and consider the deeper meaning of what we've discussed. The search for life on Enceladus is not merely a technical challenge or a scientific curiosity. It touches on fundamental questions about existence, purpose, and humanity's place in the universe. For thousands of years, humans have wondered whether we are alone. Ancient Greek philosophers speculated about a plurality of worlds inhabited by other beings. Medieval scholars debated whether God might have created life on other planets. In the 20th century, scientists began searching in earnest. First, with radio telescopes listening for signals from intelligent civilizations, then with spacecraft exploring the planets and moons of our solar system. The question of extraterrestrial life has always been as much philosophical as scientific. It forces us to examine our assumptions about what it means to be alive, to be intelligent, to be significant. If we find even microbial life on Enceladus, have profound implications for how we understand ourselves. Consider first the question of our uniqueness. For most of human history, we believed Earth was the center of the universe. Copernicus showed us that we orbit the sun, not the other way around. Galileo revealed that other planets have moons, that we're not the only world with companions. Hubble showed us that our galaxy is just one of billions. Each discovery pushed us further from the center, made us less special, less unique. The discovery of life on Enceladus would continue this trend. It would demonstrate that Earth is not the only living world, that biology is not a cosmic accident that happened only here. We would be just one branch on a much larger tree of life, a tree whose roots extend across the solar system and perhaps across the galaxy. For some people, this would be deeply unsettling. Our religions, our philosophies, our sense of meaning and purpose are all built on a sump, humanity's place in creation. If we're not unique, if we're not the reason the universe exists, then what is our significance? But there's another way to look at it. The discovery of life elsewhere wouldn't diminish our importance. It would expand the circle of life we belong to. We would no longer be alone, isolated on a single pale blue dot. We would be part of a community, a biosphere that extends beyond one world. Consider the ethical implications. If life exists on Enceladus, what obligations do we have toward it? Do microorganisms have rights? Should we protect Enceladus's ecosystem from human interference? These questions are not merely academic. They will affect how we explore, how we conduct our missions, whether we allow human settlement or resource extraction on ocean worlds. Some philosophers argue for a precautionary principle. If there's any chance that life exists on Enceladus, we should minimize our impact, avoid contamination, and tread. Others argue that knowledge itself has value, that we have a duty to explore and understand, and that we can do so while respecting any life we find. The debate parallels discussions about Earth's ecosystems. We recognize that wilderness has intrinsic value, that species have a right to exist independent of their utility to humans. But we also recognize that human needs matter, that development and conservation must be balanced. The same tensions would apply to Enceladus, only magnified by the novelty and potential significance of any life there. There's also the question of whether Enceladian life is truly alien, or whether it's related to Earth life through panspermia. Panspermia is the hypothesis that life, or at least the building blocks of life, can be transferred between worlds on meteorites ejected by asteroid impacts. We know that rocks from Mars have reached Earth. The ALH 84001 meteorite proves that. If life existed on ancient Mars, could it have reached Earth and seeded our biosphere? Or vice versa, could Earth microbes have reached Mars? For Enceladus, the scenario is less plausible. The distances are vast, the transfer times extremely long. But it's not impossible. Material ejected from the inner solar system by large impacts could theoretically reach the outer planets over millions of years. Microbes encased in rock, frozen and dormant, might survive the journey. If Enceladian life uses DNA, proteins, and the same genetic code as Earth life, it would strongly suggest panspermia rather than independent origin. Two independent origins using identical biochemistry would be an extraordinary coincidence. But if Enceladian life uses different molecules, different genetic systems, different metabolic pathways, it would prove that life can arise independently in different environments. That proof would have staggering It would mean the origin of life is not a miraculous fluke, but a probable outcome of chemistry under the right conditions. It would suggest that the universe is filled with life, that wherever we look, wherever conditions are suitable, we will find living worlds. Some scientists estimate that there could be millions of habitable ocean worlds in our galaxy alone. If even a small fraction harbor life, we're talking about potentially millions of biospheres, millions of separate origins, millions of independent experiments in evolution and adaptation. The sheer scale of life in the universe would force us to reconsider our place in it. We would no longer be the pinnacle of creation, but one species among countless others, one biosphere among millions. Our achievements, our history, our struggles would be significant to us, but would represent just one tiny thread in the vast tapestry of cosmic life. This could lead to humility, that we are small and that the universe does not revolve around us. But it could also lead to curiosity and wonder. Every ocean world, every biosphere would be a natural laboratory, showing us what life can do under different conditions. The diversity would be astonishing, the possibilities endless. There's also the question of intelligence. If simple microbial life exists on Enceladus, could complex life, even intelligent life, evolve there? On Earth, it took about 3 billion years for multicellular life to arise, and another 500 million years for intelligence to emerge. Could similar processes occur on Enceladus? The environment is challenging. The ocean is dark, cold, and isolated from the surface. There's no sunlight to drive photosynthesis, no dry land for terrestrial life to colonize, no oxygen-rich atmosphere. On Earth, the evolution of complex life required oxygen, produced by billions of years of photosynthesis by cyanob. Without oxygen, metabolism is less efficient, and energy availability limits how complex organisms can become. Most scientists believe that Enceladus, if it harbors life at all, likely hosts only simple microbial communities, similar to those at Earth's hydrothermal vents. Complex, multicellular life, let alone intelligence, seems improbable. But improbable is not impossible. Evolution is creative and unpredictable. Given enough time, given the right conditions, who knows what might emerge? Perhaps in 1 billion years, if Enceladus's ocean remains stable, life there will have evolved complexity and diversity rivaling Earth's. Perhaps organisms will have adapted to the dark, developed bioluminescence, created ecosystems as rich as coral reefs. Perhaps, in the far future, intelligence will emerge, and civilizations will arise beneath the ice, never knowing that a universe exists beyond their frozen ceiling. It's a humbling thought, the idea that intelligence independently on other worlds, that other beings could develop science and philosophy and art without any contact with us, challenges our assumptions about the uniqueness of consciousness and culture. And if intelligence can arise independently multiple times, what does that say about consciousness itself? Is it an inevitable outcome of complex information processing, a natural feature of the universe as fundamental as gravity or entropy? Or is it something rare and special, an emergent property that requires very specific conditions? These are questions that philosophy has grappled with for millennia, but they take on new urgency when we consider the possibility of finding life elsewhere. The answers will not come from speculation alone. They will come from observation, from exploration, from the actual discovery and study of extraterrestrial life. In a sense, the nature of existence itself. It's about answering the question, what is life? Is it a physical phenomenon that can be understood through chemistry and physics? Is it something more, something that transcends the material? How do we distinguish living systems from complex chemistry? Scientists have proposed many definitions of life, but none is entirely satisfactory. Life reproduces, but crystals grow and propagate. Life metabolizes, but fire consumes fuel and releases energy. Life evolves, but computer programs can evolve through genetic algorithms. Life maintains homeostasis, but thermostats regulate temperature. Perhaps life is not a binary category, but a continuum. Perhaps there are systems that are partially alive, that have some but not all of life's properties. Perhaps the boundary between life and non-life is fuzzy, and Enceladus will teach us that the distinction we've always assumed is clear-cut is actually gradual. These questions may seem abstract, but they have practical implications. If we're not sure what counts as life, how do we design our biosignature detection instruments? How do we interpret ambiguous results? How do we decide what to protect and what we're allowed to disturb? The search for life forces us to confront our ignorance, to admit that for all our scientific progress, we don't fully understand what life is or how it works. It forces us to remain humble and open-minded, ready to revise our theories when the evidence demands it. And ultimately, the search for life on Enceladus is an expression of one of humanity's noblest qualities: curiosity. The desire to know, to understand, to explore beyond the familiar. This curiosity has driven every great achievement in human history, from the first humans leaving Africa to explore the world, to the astronomers mapping the heavens, to the scientists unlocking the secrets of the atom. Now, that curiosity take Enceladus, not for profit, not for conquest, but simply to know, to answer the question that has haunted us since we first looked up at the stars and wondered, are we alone? Whatever the answer, the act of asking the question, of building the spacecraft, of flying to distant worlds to seek the truth, that act itself is meaningful. It says something fundamental about who we are as a species. We are explorers. We are seekers. We are not content to remain in ignorance when knowledge is within reach. And so we will go to Enceladus. We will sample the plumes. We will analyze the chemistry. We will search for life. And whatever we find or don't find will change us forever. Reflections and closing. As we come to the end of our journey tonight, let us reflect on what we've learned and what it means for our future. We began by imagining ourselves floating in space, 886 million miles from the Sun. Lo, Saturn and its small moon Enceladus. We traced the history of how this tiny world, unremarkable for centuries, revealed itself to be one of the most extraordinary places in the solar system. We learned about the Cassini mission and its unexpected discoveries, the bright reflective surface, the warm tiger stripes, the towering plumes of water vapor and ice erupting from the South Pole, the evidence for a global ocean beneath the ice, the detection of hydrogen suggesting hydrothermal activity, the discovery of all the essential elements for life, including the elusive phosphorus. We explored what conditions in that ocean might be like: the cold, dark water, the high pressure, the circulation driven by tidal heating, the possible hydrothermal vents, where hot water, rich in hydrogen. We compared Enceladus to other ocean worlds in our solar system, Europa and Titan and Ganymede. We examined why Enceladus stands out, with its accessible ocean erupting directly into space, where we can sample it without drilling through miles of ice. We looked at life in Earth's deepest oceans, at hydrothermal vents where entire ecosystems thrive in complete darkness, powered by chemical energy rather than sunlight. We learned about extremophiles, organisms that survive conditions we once thought impossible for life. And we considered whether similar life could exist on Enceladus. We discussed biosignatures, the signs we would look for to detect life. Amino acids with homochirality, fatty acids with biological distributions, lipid vesicles resembling say membranes, isotopic fractionation from metabolism. And we explored how future missions would search for these signs. We examined mission concepts, from the ambitious Enceladus Orbilander to faster, cheap alternatives. We looked at the technologies being developed to make these missions possible. Power systems, autonomous navigation, sensitive instruments, contamination prevention, all the pieces coming together to enable the search. We imagined what we might find: a null result, an ambiguous result, a clear positive detection, or something utterly unexpected. And we considered how each outcome would affect our understanding of life and our place in the universe. We explored the philosophical implications, questions of uniqueness and significance, ethical obligations toward extraterrestrial life, the possibility that life is common in the universe or vanishingly rare, the nature of consciousness and intelligence, the very definition of what it means to be alive. Throughout this journey, one theme has emerged again and again. Enceladus represents hope. Hope that we are not alone. Hope that life is a common and robust phenomenon in the universe. Hop, in the coldest, darkest places, far from the sun's warmth, chemistry can organize itself into biology, and biology can create the complexity and beauty we call life. But Enceladus also teaches us patience. The timescales of space exploration are vast. Cassini took 7 years to reach Saturn. Future missions will take just as long. Development of those missions takes a decade or more. From concept to result, we're looking at 20 to 30 years. For scientists dedicating their careers to this search, it requires extraordinary patience and faith that the work will pay off, perhaps long after they're gone. It teaches us humility. For centuries, we thought Enceladus was just another dead, frozen moon. Cassini showed us how wrong we were. How much else do we not know? How many other surprises await us in the solar system? How often have our assumptions about what's possible, what's habitable, what's interesting been proven wrong by actual explains on decisions we make today? Decisions about funding, priorities, technologies, decisions about which missions to fly and when to fly them. Decisions about how much we value knowledge for its own sake, exploration for the sake of discovery, the satisfaction of answering profound questions about our existence. These are not easy decisions. Resources are limited. Competing priorities demand attention. There are problems here on Earth that need solving, immediate crises that require action. It's tempting to say we should focus on our own planet before worrying about a moon nearly 1 billion miles away. But perhaps the search for life on Enceladus is exactly what humanity needs right now. A project that unites rather than divides us. A challenge that requires our best qualities: intelligence, creativity, persistence, cooperation. A goal that reminds us we're all passengers on this pale blue dot together, looking outward at a universe that may be filled with us. On decisions we make today, decisions about funding, priorities, technologies, decisions about which missions to fly and when to fly them, decisions about how much we value knowledge for its own sake, exploration for the sake of discovery, the satisfaction of answering profound questions about our existence. These are not easy decisions. Resources are limited. Competing priorities demand attention. There are problems here on Earth that need solving. immediate crises that require action. It's tempting to say we should focus on our own planet before worrying about a moon nearly 1 billion miles away. But perhaps the search for life on Enceladus is exactly what humanity needs right now. A project that unites rather than divides us. A challenge that requires our best qualities: intelligence, creativity, persistence, cooperation. A goal that reminds us we're all passengers on this pale blue dot together, looking outward at a universe that may be filled with other passengers on other pale blue dots. And perhaps on a more personal level, the search for life on Enceladus satisfies a deep human need. The need to know we're not alone. The need to understand our place in something larger than ourselves. The need for wonder, for mystery, for the thrill of discovery. In our everyday lives, it's easy to become consumed by small concerns. Bills to pay, deadlines to meet, conflicts to resolve. But sometimes it's important to step back and look at the bigger picture, to remember that we live in a vast and ancient universe, that billions of years of cosmic evolution have led to this moment, that we are made of atoms forged in the hearts of dying stars, that we are stardust that has gained the ability to contemplate its own existence, and that out there, in the cold darkness, circling Saturn, there might be another place where the same cosmic chemistry has created life. Different from us, adapted to an alien environment, but alive in some fundamental way, connected to us through the deep physics and chemistry that governs all matter and energy. If we discover that life on Enceladus, it will be one of the greatest moments in human history. We will remember where we were when we heard the news. We will tell our children and grandchildren that we lived through the time when humanity learned it was not alone in the universe. But even if we search and find nothing, even if Enceladus proves to be sterile, the search itself will have been worthwhile. We will have developed new technologies. We will have trained a generation of scientists and engineers. We will have inspired millions of people to look up at the night sky and wonder. We will have demonstrated that humans are capable of coming together to pursue knowledge, to explore, to seek truth. And we will keep searching. Because the question is too important to give up on. Because somewhere in this vast universe, there must be other worlds where life has taken hold. And eventually, whether on Enceladus or Europa or Mars or a planet circling another star, we will find it. As you drift off to sleep tonight, think about that small moon. Think about the ocean beneath the ice. Think about the plumes erupting into space, carrying secrets from the deep. Think about the spacecraft that will one day land near those plumes and unlock those secrets. And think about what it means that we as a species have reached the point where such a mission is possible. That we have the knowledge, the technology, the will to send spacecraft across the solar system to search for life. That we care enough about the question to invest decades and billions of dollars in answering it. This is what humanity can do when we work together toward a common goal. This is what we're capable of when we let our curiosity guide us. This is our potential, our promise, our future.